This conference will now be recorded.
Hello everyone. Hello everyone. Am I audible?
Yes, you are.
Yes,
Okay,
yes.
thank you. Thank you. Thank you very much. I hope everyone is here and we'll start. Let me give a brief introduction. A very good morning, good afternoon, and good evening to one and all present here. Before proceeding further, first let me introduce myself. I'm Emily Rees from pleased to welcome you to this conference. Firstly, I would like to thank the researchers from their respective fields of research for taking their precious time out and making to this event. It will be my pleasure to introduce to you all the speakers who came to attend today's webinar to share their knowledge. Before we begin with today's sessions, please allow me to deliver a brief introduction about our organization and further instructions to proceed. Scisynopsis conferences provides the opportunity to discuss latest cutting-edge clinical and basic scientific research from all the elements and fields of life sciences, medical, clinical, chemistry, technology, medicine, pharma, management, engineering, and technology. Gain the experts' opinions on current research and issues across the breadth of science and engineering. We remain curious and passionate towards providing a forum for scientists, distinguished researchers from universities, research institutes, companies, laboratories with the latest knowledge on integrating topics with wide range of great events to get the knowledge that can reshape the today's world. Thank you once again to all the attendees of today's conference and hope you will enjoy this and gain knowledge from the sessions. Now, as some of our attendees are new to GoToMeetings app, so I will explain you the important settings and procedure how to begin with that. As you have joined through the link provided, you can see the screen where you can find four icons at the bottom of center of the screen. Mic, camera, screen. So mic button, click on that to mute or unmute yourself. So I request you all to stay muted while our speakers are presenting their research work so that it doesn't cause any disturbance to them. Camera, you can use this button to share or unshare the web camera. If you have the option to share the web camera, you can do it, or else it is completely your choice. Screen, you can use this button to share your screen at your schedule. When I call your name from my side, I will make you the presenter. When I will give you the access to share your screen, then you need to click on this button and you will find a pop-up window which will ask you to share the screen and you can proceed further. For MacBook or Apple devices, once I make the presenter, then you need to give permission to share the screen in your system preferences. After that, you need to log out from the session and need to join again from the same link and share screen for presentation. Leave. This is your last icon. Clicking on this button will leave you from the session. On the top right corner, you can find three icons: people, chat, settings. The people which shows you all the attendees of webinar. Chat, in this option you can chat with any other participants or with me for any queries. Settings, you can use this button to check for the settings for your speaker and microphones. So as mentioned, kindly remain muted during the presentation so that the presenters don't get disturbed, and for any questions you can ask me or can write in the message box too. So as mentioned, kindly remain muted during the presentations so that the presenters doesn't get disturbed. Finally, I would like to request you all to give a brief introduction about yourself before starting with sessions so that we can know about you virtually. Now let us move into our sessions. The first presentation is by the first presentation is a keynote presentation by Dr. Giovanni Magno from the Polytechnic University of Bari, Italy. Hello, Dr. Giovanni Magno. Are you ready with your presentation?
Yes. Hello,
Oh,
everybody. And yeah,
okay. Yeah,
I've not, yeah,
Yes, I'm
yes.
making you the presenter. Please click on the share button to share your screen.
Yes. Let me see. Okay. So do you see my screen?
No, Dr. Magno, not yet.
Okay. What should I? Can,
Kindly click on the share button. After that, you can find a pop-up window where
yes.
yes, okay.
So do you see my screen
Yeah,
now?
yeah. Your presentation is yes, it's perfect.
Okay. Thank you very much.
Thank you.
So thank you for the introduction. I'm Dr. Giovanni Magno from Politecnico di Bari, and I'm a researcher in electromagnetic fields. I will present a keynote speech on efficient integration of plasmonic structures, especially devoted to integration of the structures inside photonic circuitry. So let's get started. In today's world, using light signals is crucial for handling complex tasks like computing, information processing, and communication. This is especially vital as the demand for data exchange continue to grow. So how do we meet these demands effectively? All optical solution can undoubtedly offer several key advantages. The solution see one of the highest expression in photonic integrated circuits, or PICs for short. The goal of PICs is to deliver an analog of electronic integrated chip that could perform all the required computational processes using photons while being space and time efficient. The SPICs are designed to create complete optical system and make it easier to use various optical function, all the way from generating light sources to modulating and detecting signals, including coupling, polarization control, spectral and spatial filtering, focusing, splitting, isolation, and modulation of light. They also borrow part of the manufacturing techniques from microelectronics to achieve two important goals. They allow us to control the way optical signal moves in a two-dimensional system with minimal losses. And they make it simple to connect multiple functions in a series or parallel arrangement without needing bulky free space optical components. They exploit materials with a high refractive index and guiding structure to reduce the size of features typically realized in free space optics. Guided planar optics, of course, it's a game changer since it lets us integrate compact optical elements even when their lateral dimension are as small as the wavelength of light in the material. However, there is a limit on how small we can go due to diffraction limitations. This speech serves a dual purpose. First, it wants to explore strategies for integrating plasmonic structures on dielectric waveguides. And second, it aims to highlight the different electromagnetic function that this integration can unlock within the framework of photonic integrated circuits. So, plasmonics is a field capturing widespread interest since the early 2000s. It boasts the remarkable ability to shrink light down to the subwavelength scale. And this is possible thanks to the surface plasmon polaritons, which arises when light couples with free electrons in certain plasmonic metals, like, for instance, copper, gold, silver, and aluminium. Why surface plasmon polaritons are important? Well, it's all about manipulating light at a scale smaller than the wavelength. The possibility to tightly concentrate and control electromagnetic fields deep into the subwavelength world helps shrinking optical functions, boosts nonlinear interaction, offers control over heating, sensing of the surrounding with enhanced sensitivity. For instance, it can reduce the size of photonic circuits and aid ultrafast on-chip signal processing. But of course, this comes with challenges, which are mainly due to high optical losses and difficult excitation of surface plasmon polaritons. Well, let's give a little spoiler here. The solution to these challenges rely on smart, sparingly integration of plasmonic elements within waveguide structures and more generally in photonic integrated circuits. So, combining photonic integrated circuits with plasmonic structures let us benefit from low losses in dielectric waveguides while maintaining the typical plasmonics compactness. In summary, the trick is using plasmonic components only where they are needed and connecting them through effective integration in low losses systems. Plasmons manifest into two distinct forms. The propagating plasmons on metal surfaces and localized plasmon within tiny metallic structures. Propagative surface plasmon polaritons emerge at an interface where metal and a dielectric material meet, and they possess a unique field profile resembling a transverse magnetic wave with the primary electrical field component being perpendicular to the interface. The field shows an evanescent profile on each interface side. Here we find the surface plasmon polariton dispersion curves for air and gold interfaces and for indium phosphide and gold interfaces, where omega p represents the plasma resonance in the metal. These curves unveil three fundamental characteristics of surface plasmon polariton. Firstly, the dispersion curves remain below the light lines in the medium. This means that the surface plasmon polariton travels with a higher wave vector than an electromagnetic wave inside the same medium. Secondly, when the frequency approaches the plasmonic resonance, the dispersion curves becomes almost flat, almost horizontal. And this implies that the plasmonic mode moves very slowly with an almost zero group velocity. And it becomes highly confined near the metal, which means we feature high ohmic losses. And thirdly, plasmonic resonance is strongly dependent on the surrounding medium. Various plasmonic waveguides supporting propagative modes have been developed, as shown in the figure on the right here. Some of these are designed for long-range propagation by minimizing the direct interaction between wave energy and the metal. For instance, this is achieved through coupling the two surface plasmon polariton traveling on the two sides of a thin metallic film or within a thin metallic slot waveguide. This coupling results in two supermodes appearing here. The so-called long-range surface plasmon polariton having a symmetrical phase profile and a reduced losses since the interaction with the metal is reduced. And dually, we have the short-range mode with a asymmetrical phase profile and increases losses since the interaction with the metal is maximized here. The question is how to couple plasmonic waveguides with dielectric waveguides inside photonic integrated circuits. We have two typical approaches. Transitions, as in figure B and C, like for instance evanescent coupling or grating couplers, and butt coupling. This one, the latter, is also known end-fire coupling, and generally speaking is less effective with respect to the other method. This is due to mode shape mismatch between plasmonic and photonic modes, so we don't discuss it here further. So let's focus to other methods based on transition. The physical mechanism behind this method becomes clear by observing the dispersion curves of the involved mode. In figure B, a plasmonic waveguide is placed in close proximity to a dielectric waveguide via vertical stacking of different layers. Here, the dielectric waveguide mode has an effective index that is naturally higher than the refractive index of the surrounding dielectric material, and thus the guided mode wave vector Kd is higher than that of a plane wave propagating in the superstrate. These allow for direct excitation of the surface plasmon polariton on the waveguide. This results in the mode coupling, which generates two supermodes with hybrid photonic plasmonic nature, which features a symmetric and antisymmetric field distribution with different effective indices. And the length over which this coupling occurs, knowing as the coupling length, is determined by this indices difference. After propagating through the coupling regions for a distance equal to the coupling length, the energy of the injected in the dielectric waveguide is completely coupled to the plasmonic waveguide. And this mode coupling is referred to evanescent coupling because it involves the evanescent tails of the guided modes. The greater the difference in the supermode indices, the short will be the coupling length. For example, Delacour et al. Proposed the coupling of a silicon on insulator waveguide with a copper plasmonic slot waveguide at 1.53 micron, which result in an experimental coupling length of less than 1 micron and an estimated coupling efficiency ranging between 16 and 17%, with a configuration working in the neighboring of the phase matching condition. In another example involving polymer waveguide, I previously demonstrated that the coupling between a polymer on glass waveguide and a buried plasmonic waveguide in the visible regime can achieve a coupling length of 5.3 micron and a coupling efficiency as high as 89%. Using silicon on insulator waveguide, it's particularly interesting since the phase mismatch in this case between the two modes is higher, since the higher in the contrast in indices. So in this case, in order to propagate, to allow the excitation of long-range modes, it would be desirable to exploit layers of dielectric materials with higher refractive indices that encapsulate the plasmonic waveguide in order to help satisfying the phase matching condition. This will result in a very, very high coupling efficiency and in a shorter propagation length. If the phase matching condition cannot be met directly via evanescent coupling, the dielectric guided mode must interact with a complementary structure to increase the wave vector module up to that of the plasmonic modes. This can be achieved using a periodic grating which generates special harmonics to excite the surface plasmon polaritons at the dielectric metal interface. The grating can be designed to provide the missing component for the plasmon excitation. In this case, the strong mismatch between the dielectric and plasmonic waveguide can also be compensated by utilizing successive grating with decreasing period that can be used for a kind of progressive adaptation of the modes, although this may result in a longer and potentially very lossy transition. In this example, Tetienne et al. Demonstrated an integrated coupler using metallic grating for the transition between a semiconductor waveguide and a plasmonic gold film at 1.3 micron, achieving a 5.5 micron transition and a global excitation efficiency of 24%. So usually grating couplers are slightly less effective than evanescent couplers. Besides propagating plasmon, we also can take advantage of localized surface plasmon. This form of plasmon arises in small metallic structures with dimension comparable or smaller than the wavelength. When a field interacts with a metallic nanoparticle, the charge density in the conduction band will follow the oscillation of the field, creating a current and an effective accumulation of charges. This collective behavior can be described using a Lorentzian oscillator, and these produce a considerable enhancement of the electric field in the close vicinity of the particle, the metallic particle surface, which can be exploited, for instance, in sensing. Just to give an example, this enhancement is at the basis of the SARS effect. The plasmonic modes supported by an individual meta-atom are then modified by the presence of neighboring particle through a plasmonic coupling similar to the hybridization of atomic orbitals. Plasmonic coupling yields a shift in the resonance frequency and can strongly increase the field enhancement. The response to electromagnetic excitation of metal nanoparticle is characterized by polarizability, which is a very defined mathematical expression when we refer to simple shape and when the surrounding medium is uniform. So when you excite a dipole in a plasmonic nanoparticle, the dipole radiates an electromagnetic wave at the same frequency, and this emitted wave can in turn excite another plasmonic nanostructure through the so-called dipolar coupling. In this way, assemblies of plasmonic nanostructure can support collective modes and transfer energy from one particle to the next. You can, for instance, calculate the dispersion curve of a so-called chain mode. And this can be done, for instance, numerically. Here we see the dispersion curve of a plasmonic chain made up of gold nanocylinders with elliptical cross-section that are placed on a semi-infinite silicon substrate. The chain modes share some similarities with the propagative surface plasmon polarity. It is located below the light line. It has a nearly horizontal slope. In other words, the chain modes propagate through dipolar coupling as they were in a waveguide. So the plasmonic chain behave as an effective waveguide. And we can also efficiently transfer energy from a dielectric mode into a plasmonic chain waveguide by using evanescence coupling. Usually here, strong coupling enables a very high coupling efficiency. In the figure, we have a plasmonic chain integrated on a silicon or insulator waveguide or on a silicon nitride waveguide. And here we have the independent dispersion curves of the dielectric waveguide and of the plasmonic chain. And when we put the two structures in close contact, strong coupling appears and an entrecrossing appears in the crossing point of the separated structures. And these allow for a very efficient excitation of the supermodes of the structure. And so it allows us to transfer the energy into the plasmonic chain in a very short coupling length, since the coupling length depends on the difference of the effective indices of the supermodes. And since here the gap is very broad, the coupling length is very short. So depending on the wavelength, the fundamental TE modes of the dielectric waveguide here can be completely transferred to the chain, starting from the fourth of the fifth metal nanoparticles. So it results in a coupling length of around 600 nanometer, and a coupling efficiency near to 99% in only 5 metallic nanoparticles in the infrared. If we work in the visible regime with a silicon nitride waveguide, the same efficiency can be reached in about 8 nanoparticles. So the coupling length would be of 800 nanometers. Coupling between plasmonics and silicon on insulator waveguide introduce additional distinctive characteristics. Firstly, over a wide range of frequency, the supermode propagates in a vortex-like manner, which is associated with a slow mode behavior since the hot mode dispersion curve becomes almost flat. Additionally, these vortices can be characterized by their phase profile along the chain, which give rise to a characteristic phase carving behavior. Secondly, due to strong coupling, supermode can be excited beyond the light lines of the different materials surrounding the plasmonic chain. And this means they can be excited as radiative mode above the light line of the confinement layer or below the highest index material light line, which is silicon here. So this means that plasmonic mode hybridation can modify the radiative or guided nature of modes and extend the possible frequency range. Okay, so after this introduction, let's explore the application of surface plasmon in photonic integrated circuitry, which offer the potential to enhance various photonic functions thanks to the ability of plasmonic to concentrate light at some wavelength scale and enhance local fields. We will consider 4 different examples. The first example is sensing, and sensing with plasmonics has come a long way. In terms of sensitivity and compactness, plasmonic sensors have outperformed traditional optical sensors. Thanks to the interaction of the analytes with their sensitive evanescent fields, analytes can be perceived as a variation in the environment refractive index. To date, several configurations have been proposed to retrieve this variation, which exploit, for instance, spectroscopy, power, or phase-based approaches. However, one of the most important weaknesses of long-range plasmonic waveguides is then that when a thin metal stripe is set in an asymmetric environment, which is typical in sensing scenarios, the phase mismatch at the two interfaces can forbid the formation of long-range modes. And so it forbids the exploitation of such sensible modes. An elegant way to overcome this problem is represented by the use of hybrid dielectric loaded plasmonic waveguides, as the configuration shown here. This consists of a metal stripe located on a substrate which underlines a thin dielectric layer, and by properly tuning the geometrical parameter of the waveguide, such as the thickness or the total length, is it possible to maximize the sensitivity for certain specimen. This configuration, for instance, can be suitable for sensing gases or liquid variation with a very high resolution. However, the total device length exceeds 300 micron and cannot be further miniaturized. To increase the compactness, we evolved into using localized surface plasmon, such as metallic nanostructures array on waveguides. And in this kind of structure, we can take advantage of the strong coupling discussed before between plasmonic chains and waveguides. Here in the right figure, we have an example of such guided plasmonic sensor with a chain of 5 metallic nanoparticles integrated on top of a waveguide, which is placed inside an integrated microfluidic system. And below, we see the optical power as a function of the wavelength. This shows the spectral shift in response caused by the presence of, in this case, thiol molecules, which interact with functionalization of the metal and form an equivalence layer with a specific thickness and indices. With these integrated sensors, it's possible, for instance, achieving sensitivity of about 270 nanometers over refractive index unit. And the second application that can be analyzed is tweezing of nanoparticles. Here, the basic idea beyond optical tweezers involve focusing laser beam, which generated 2 types of different forces on an object interacting with the beam, the gradient force and the pressure force. The gradient force pulls the object towards the region with the highest optical intensity, with a certain variable stiffness depending on the beam profile, while the pressure force pushes the particle along the direction of the laser beam. In near-field plasmonic tweezers, plasmonic structures create powerful gradient force due to the higher field confinement. However, in this type of tweezer, manipulating particle through this is not as easy as in far-field tweezers, since the trapped object will follow the position of the hotspot in the near field. And manipulability in this case require to ask for reconfigurability of the position of hotspots, which is not trivial to be attained on plasmonic resonators. And in literature, different geometry of plasmonic structures have been proposed as nanotweezers, such as 2D arrangement of nanodiscs or nano apertures, nanowires and bow ties antennas, or even simple flat metallic films. When we integrate plasmonic nanoantennas on dielectric waveguides, their true power discloses, and this element can be then integrated in photonic integrated circuits dedicated to lab-on-chips, for instance, which can be exploited to capture or release a single nanoparticle inside a microfluidic systems, or even allow a group of nanoparticles to interact and auto-assemble. Here show a few examples. In figure A, we have a matrix of plasmonic disks integrated on a multimode waveguide, which has proven to be capable of trapping beads with 1 micron diameters with a quite remarkable stiffness. And in figure B, an integrated bow tie structure concentrates light in the narrow gap, which is ideal for trapping particles having smaller size. In this case, we are able to trap down to 20 nanometer diameter particles with a very impressive force. In figure C, an integrated plasmonic chain, which I've shown be capable of maximizing the coupling, can be used for tweezing for tweezing too. And in this case, we are able to trap polystyrene beds having 500 nanometer in diameter with also a very high force and impressive stiffness. If we need to trap even smaller particles, we can exploit, for instance, two-element chains in which we can confine the fields more tightly by reducing the dimmer's gap. And here, the trap stiffness and the force and the potential depth increases as the dimmer gap shrinks. Here, the video on the right shows the behavior of polystyrene beds when trapped at two different power levels. At lower power level, we can achieve reversible trapping, while at higher power level, due to the strong heat generated by the plasmonic resonator, we see non-reversible trapping in which a group of particles will auto-assemble around the resonator with a very strong force. And taking advantages of plasmonic chains, we can not only trap nano-objects, but also manipulating them along the chain itself. As we discussed before, in this structure, we have strong coupling, and the coupling length strongly depends on the wavelength close to the plasmonic resonance, which in this example occurs around 1.5 microns. And this allows us to control the position where the most intense hotspot occurs along the chain. In this way, we can reconfigure the position where the trapping occurs and control the position of a small object that is captured by this device only by changing the injected wavelength. Okay, I think how many minutes I have left? I guess. Well, I will be fast. So the third application on which we can exploit plasmonic resonator inside photonic integrated circuits are nanoantennas, which can be used for beam shaping and steering in synergy with advanced feeding scheme, which can be useful for control the phase of light going through the emitters. And this control can be further miniaturized in plasmonic chained coupled with dielectric waveguide, where the direction of emission can be controlled as a function of the wavelength without any further control element. And also plasmonic nanoantenna into photonic integrated circuits hold potential for short-range on-chip and chip-to-chip wireless communications. Various types of plasmonic antennas have been proposed for this purpose, such as integrated Vivaldi antenna, which allow for strong coupling of the plasmonic excitation and then tapering toward radiative modes that can be then captured by a receiver made in the same manner. And to increase the efficiency of communication, we also can leverage arrays of plasmonic antennas in this regard. Well, we have no time to speak of the fourth application I had in mind, which concerns non-reciprocal plasmonic device for integrated circuits. And so let's go to the conclusion. So the fusion of plasmonic structure with photonic waveguide represents a significant stride toward the miniaturization of photonic integrated circuits. Efficient methods for connecting the structures are pivotal in achieving high integration efficiency. We discussed about evanescent coupling between dielectric and plasmonic waveguides, which enables efficient energy transfer through supermode beating, which yield a remarkable coupling efficient, often exceeding 19% over a very short propagation distance. And this engineering enabled the utilization of plasmon within a photonic circuit with moderation only when needed, offering an optical balance between compactness and enhanced physical effects, as well as minimized losses. Numerous and diversified applications can be considered, especially thanks to the ease of technological processes. This integration has been presented here in a broad spectrum of application, which encompasses biosensing, optical tweezing, nanoantennas, and well, I had in mind also to present non-reciprocal elements, but we are out of time. So in a nutshell, the fusion of plasmonic structure with a photonic waveguide open up an exciting avenue to enhance the functionality of photonic integrated circuits. So thank you very much for your attention. If you have any question or curiosity about this presentation, I will be happy to answer.
Thank you, Dr. Ivani Magno, for your wonderful presentation. Does anyone have any query?
Yes, I have a question.
Yes, please.
First of all, very nice lecture. I just want to ask about the coupling efficiency.
Thank you.
Did you check the back reflection in this approach?
Yeah, when you work at phase matching condition, the back refraction is almost zero. It's very, very low. As soon as you get far from the matching condition, you get back refraction. And this is the main advantage of using evanescent coupling instead of bad couplings. Because in bad couplings, you have a very different mode mismatch, which leads to a very strong back reflection. And this is also in a less degree observed when using diffraction grating. But in an evanescent coupling, when you are working at the phase matching condition, usually your backscattering is almost zero.
Okay, thank you. Did you also fabricated it?
Yes. For instance, we fabricate these structures. This one, I mean, which we exploited in demonstration of integrated tweezing. Okay, and
okay, thank you.
You're welcome.
Hello.
O-
Hello, Dr.
Okay.
Magno.
Hello.
Hello?
Yes, yes, Dr. Magno, thanks for your presentations. And I have some queries. Can I proceed?
Yes. Yes, yes, of
Uh,
course.
Actually, I am more interested about plasmonic nanoparticles. Actually, so in this case,
Mhm.
you showed that this plasmonic can be proceed in two ways, that is horizontally and also through vortex. And I actually want to know what are the most determining factor to control their pathways, means which is the most yes, in this slide you show that it can also proceed by vortex like structure. So what are the more deciding factors for controlling those propagation?
Y- You mean you want to minimize the vortices?
Yes.
Well, as long as you work in frequency where the dispersion curves becomes flat or flattish,
Okay.
this means that you are approaching a slow light regime. Okay,
Hmm.
so light travels with a lower group velocity, and vortices are naturally a consequence of this. So in any structure in which you have slow light, you usually can observe vortices.
Okay. Okay.
So
And
the degrees of formation of vortices depends on the region of the dispersion curve you are working on. If you work here, for instance, far from the slow light regime, you will observe almost no vortices. If you work near the flat line, you will observe a higher degrees of vortices.
okay. Okay. Thank you. And another questions, actually, you shown that size of the nanoparticles has also effect on controlling these plasmons. So uh, I want to ask you uh, if there is any kind of minimum distance or maximum distance limit to control this plasmonic means LSPR effect. If I
Yes,
if I want
it
to attach
is.
with
And
kind of semiconductor in that case,
mhm.
so what?
So what we have to take in mind that size of the nanoparticle constituting the chains
Mhm.
and distance of the chain itself lead to different behavior. I mean, the size of the plasmonic chains, I cannot find the right, okay, here. The size of the element controls the position where the resonance occurs.
Yes.
Okay, while the period of the chain will control the behavior of the chain itself. So if the period is small enough, you will have dipolar coupling between the elements. So it will work as an effective waveguide of
So
plasmonic modes.
yes, my question
If
is in that
the
case,
period
what?
is big enough,
Okay.
if the period is big enough, it will work as a grating, no more as a as a waveguide.
Hmm. And yes,
So
in
you
that
can
case, what
exploit
will be
the
the
behavior, for
means
instance.
chain length? That plasmon chain length, what will be the maximum plasmon chain length?
The length of the
Yes,
the
plasmonic
maximum
chain.
length.
Yes,
You
yes,
mean the number of elements that you can
yes,
use? Well, this is up to
yes.
you. I mean, you have. Um, I don't know if I have a longer an image of a longer chain here, but no. Well, we simulated up to 200 elements
Hmm.
chains, and of course you have a decreasing power during the propagation due to the ohmic losses. So your interest is to make the chain as shorter as possible. But of course,
Okay.
it depends on the application.
Hmm.
So if you want, for instance, radiate fields, you can consider longer chain, as
Hmm.
in this example.
Okay.
If you want to tweeze or sense, your interest is to consider shorter waves, shorter chains. Sorry.
Okay. Okay. Hmm. Okay. Thank you. Thank you so much for your answers.
Yeah, you're welcome. You're welcome.
I hope no more queries. Okay. Thank you once again, Dr. Giovanni Magno, for your wonderful presentation, and that was a great discussion too. So let's move on to the
Thank you
next
for your
presentation.
invitation.
Thank you, doctor. Okay, let's move on to the next presentation. That is also a keynote presentation by Dr. Paulo de Moraes from Catholic University of Brasilia, Brazil. Hello, Dr. Paulo. Are you ready with your presentation?
Yeah. Hi there. Yeah, I'm ready here, waiting for.
Okay,
Uh,
I'm making you the presenter. Please click on the share button to share your screen. Hello everyone. I think there is a technical issue with Dr. Paulo's end, so let us wait for him for a few more minutes. I hope you understand. Thank you.
there. Can you hear me, please?
Hello. Yes, yes, you're audible, Dr. Paulo. Kindly click
Yeah,
on the share button and then follow my instructions.
yeah. Okay. I
Yeah,
think
yeah. After
I'm going
clicking
to
on the
get
share,
there.
yes, yes. Yeah,
Is
your screen is visible. Please make it a full screen and
okay.
start your
Let me.
presentation.
Uh, is it there, the full screen, please?
Yeah, yeah, that's perfect. Please go ahead.
Okay. Okay. Thank you very much for today. I guess I should do a short presentation of myself. So very briefly, I was with the Institute of Physics, University of Brasilia for 36 years. And then after that, I moved for 6 years to China and back to Brazil in 2018. I joined the Catholic University of Brasilia. This is my primary affiliation today. Okay, today I'm going to talk about magnetic hyperthermia and one way to control the operating temperature of the magnetic hyperthermia. So here is my roadmap for today. First, I would like to quickly review what the hyperthermia is and what is good for. And then I will switch to magnetic hyperthermia. And very quickly, I'm going to comment about the basics of magnetic hyperthermia and shortly about the instrumentation. Then next step will be the biggest challenge of the magnetic hyperthermia. And then I'll show you the difference between thermal ablation and thermal sensitization regarding cancer treatment. And then to overcome the biggest challenge, I will show you two possible solutions. One from the instrumentation itself and the other one from the sample engineering. And then some important magnetic sample morphology. So the first point that I want to mention to you, it's a very old statement made by the Greek Hippocrates. So it's about 25 centuries ago. Hippocrates is considered the father of the modern medicine, actually. So what is written in the screen is written in Latin. And for those which are not familiar with Latin, let me show you the English translation of hyperthermia. It says that those diseases which medicine do not cure, knife cures. Those which knife cannot cure, fire cures. And those which fire cannot cure are to be reckoned wholly incurable. So that statement was a very old statement indeed. But even at the time of Hippocrates, uh, it was believed that hyperthermia, which means increasing the temperature, could be used as a therapy, actually. So the modern hyperthermia today is performed using nanoparticles. And there are two ways. So we can use magnetic nanoparticle, like iron nanoparticle, but also we can use metallic nanoparticle, like gold, silver, or even platinum nanoparticle. So one way the hyperthermia is driven by magnetic properties, and the other way hyperthermia is driven by the optical properties of uh, metallic nanoparticles. The big difference, although, between the two approaches is in regard to the remote manipulation and remote heating. So magnetic hyperthermia provides not only remote manipulation but also remote heating, which are very important features of this approach. On the other way around, the use of metallic nanoparticles by exciting optically the nanoparticles, it does not permit remote manipulation, and also it does not allows you to perform remote heating. So the difference is really big. So in regard to magnetic hyperthermia, how can we shortly describe the magnetic amplifiers? In other words, how can you manipulate magnetic nanoparticles remotely? If you see here, what you need is the DC susceptibility of the nanoparticles. And at the same time, you need a gradient of the applied magnetic field. Once you have the gradient of magnetic field and the response of the magnetic nanoparticle, you can manipulate the system around. So you can move the nanoparticles around, and then you can bring them to the site that you want to stick the nanoparticles and perform the magnetic hyperthermia. On the other way around, so the heating, the remote heating, you need to apply AC external field, and then the magnetic nanoparticles should respond using the AC susceptibility. But also, this is the characteristics of the magnetic nanoparticle. Externally, you have to apply AC field, and those are the characteristics of the AC field, the frequency and the amplitude of the AC field. Besides this, of course, you have to perform the treatment or the application of the AC field for a certain period of time. And also you are going to heat the sample. So you're going to increase the temperature using magnetic hyperthermia. And then you need the specific heat of the system you are increasing the temperature. So these are the basics, ideas, and how you can provide remote manipulation and remote heating. So very shortly, what is the basics of magnetic hyperthermia? So we are talking about magnetic nanoparticles, and then they all have a magnetic moment. But say the nanoparticles are suspended in a fluid, and then if there is no applied external field, the magnetic moment of nanoparticles are oriented randomly. In other words, without external magnetic field, the net magnetization is zero. However, if you apply an external DC field and then nanoparticles align with the external field, and then magnetization of the net magnetization of the sample is not zero. However, if you shut off the field and then the magnetic moment of nanoparticles starts to disalign, and then after some time they came back to the initial condition of randomly oriented. Okay, there is, of course, a typical time from the system to come from the oriented sample to randomly oriented nanoparticles. Okay, this typical time depends actually from the two processes. The relaxation of the magnetic moment with respect to the easy axis of orientation of the nanoparticles, and also the typical relaxation time relate to the reorientation of the nanoparticle inside the medium. So the combination of the Brownian relaxation time plus the Néel relaxation time gives you the effective relaxation time. So this relaxation time effective is very important when you compare with the time of inversion of the AC applied field. Remember, the typical inversion time of the AC field scales with the frequency of the AC field. It's just the inverse. Then, if you are working in a condition that the typical inversion time of the AC field is higher than the effective relaxation time of the nanoparticles, the hysteresis curve, it shows no hysteresis area. So the curve is not open, it's closed, which means the magnetic moment of the nanoparticles it follows the AC field coherently. However, if you change this situation in such a way that the typical inversion time of the AC field is smaller than the typical relaxation time of the magnetic nanoparticles, the hysteresis curves just open up, which means the magnetic moment does not follow the external applied field anymore. It lags behind. And then it dissipates heat. And the heat dissipated from this process scales with the area of the open hysteresis cycle. This is exactly the heat using by the magnetic hyperthermia process. Okay, just shortly, how is the instrumentation to perform magnetic hyperthermia? Of course, you have to have your sample with magnetic nanoparticles in there. And then you have to insert your sample in between, inside a coil where you apply a AC current. So electronically you can apply AC current and then generate AC magnetic field. So your electronics provide you a way to control the frequency and also the amplitude of the AC field. At the same time, you need a temperature sensor to record the temperature and then make probably a feedback to control your electronics in terms of frequency and the amplitude of the magnetic field. But also you have the sample inside, and those are the characteristics of the sample: specific heat and AC susceptibility. So combining all these characteristics and performing your applied AC field for a certain period of time, you can estimate the rising of the temperature by this equation, roughly this equation. However, there is a very important point if you are going to apply magnetic hyperthermia for clinical treatment as a clinical therapy, which is called the Atkinson criterion, which says the product of the frequency and the amplitude of the AC field cannot overcome this typical value 4.85 times 10 to the 8 ampere per meter per second. So if you go higher than these, the patient or the animal which are submitted to magnetic hyperthermia becomes to be uncomfortable, which means is an extra heating of the body. So you're not heating only the point where the magnetic nanoparticles are, but also you are heating the whole body. So this is a very important criterion as far as the use of magnetic hyperthermia as a therapy. Okay, let me show you how is the biggest challenge for this therapy. So I'm going to take just a brief description of this experiment performed by the group of the German group in Vienna. So what they did at the very beginning of using magnetic hyperthermia for cancer treatment, actually they took a mice, they implant a tumor in the side of the body, and then they injected magnetic nanoparticles in the tumor and apply AC external field. And then they follow the temperature of the tumor and the temperature of the animal's body, and they realize, they measure that the temperature increases in the tumor like this curve, getting roughly the asymptotic or the operation temperature in about 250 seconds. And the saturating temperature was around 70 C. So here is a very important border that splits the higher temperature end above 43, 45 C, where you perform what they call thermal ablation. Thermal ablation induces necrosis in the tissue. However, if you are operating around 43 and 45 C, you just perform thermal sensitization. Thermal sensitization just triggers the apoptosis of the cells. So the biggest challenge of magnetic hyperthermia is to be able to operate the system around 43 and 45 C in such a way that you do not perform thermal ablation. You just perform thermal sensitization. What is the difference between one and another one? So in the thermal ablation, you induces necrosis. And it means that the temperature is so high that it breaks down the cell membrane. And of course, it releases the cell content, and it induces a huge inflammation in the animal. So this is not a desirable situation, because if the animal is holding or bearing a tumor, so it is already immune suppressed animal. And if you include inflammation, you are going to stress even further the immune system of the animal. On the other way around, if you keep the operating temperature around 43, 45, you just do what we call thermal sensitization, and then you damage the mitochondria. Once you damage the cell's mitochondria, the cell triggers the process called apoptosis. So it's a death which is a programmed by the cell itself. So we better stick on this condition to use magnetic hyperthermia as a therapy. Let me explain a little bit better the experiment performed by Ingrid Huger in Vienna. So here is a better picture of the animal with a tumor on the side of the body. What they did, they injected magnetite nanoparticles about 10 nanometers in diameter. It was coated with dextran, so to make it more biocompatible. And then they applied external AC field operating at 450 kilohertz and 140 millitesla. They did a single treatment, and the treatment performed by about 12 minutes. So about 1 week later, you can see complete remission of the tumor. But this was tumor ablation. Let me show you a different situation here, which is the tumor sensitization. There is a very interesting paper by the Japanese group, and what they did in their experiment, they use a rat and they implant tumors on both sides of the body. However, in only one tumor, they injected magnetic nanoparticles. What was the magnetic nanoparticles? Also magnetite, about 10 nanometers in diameter, but included in a liposome. So it's a magnetoliposome actually. And what they perform, so they apply the AC field about 118 kilohertz, 380 millitesla. they did the treatment 3 times in sequence, and the treatment was performed at 30 minutes uh, each day. So after 28 days, what you see is complete remission of tumor. However, what is very interesting, not only the tumor they inject the magnetic nanoparticles, but also the tumor they did not inject magnetic nanoparticles. So they explain this outcome. In the tumor, they injected magnetic nanoparticles. It was performed an actual thermal sensitization. You can see the temperature, the operating temperature around 44 and 45 C. So actually, it triggers apoptosis of the cancer cells. However, when the cancer cells release their material in the body itself, uh, this is what the authors claim, the body itself, the immune system, just fabricate a sort of its own vaccine against the tumor. And this on-site fabrication of vaccine by the immune system just make complete remission of the other tumor. So this is a very, very interesting. It shows, this experiment shows the possibility of a personalized medicine that you can stimulate the body to fabricate vaccine by its own tumor. So very interesting approach here. So what are the solutions to perform actually the thermal sensitization, which means you can drive magnetic hyperthermia and keep the asymptotic temperature, which means the operating temperature around 43, 45, and guarantee that you are providing thermal sensitization instead of thermal ablation. So we have solutions from both sides. We can control the system by instrumentation. So you have the electric control, your circuit to controlling the coil that apply the AC field, but also you need a very important temperature sensor. So the temperature has to record the temperature in real time, and also it needs to cover the whole tumor homogeneously. So in other words, you have a full picture of temperature distribution in the tumor. This is a very, very, very big challenge, actually. On the other way around, you can control the thermal sensitization by engineering the magnetic nanoparticle, by choosing the material, choosing the shape of that material and the size. So here is a proposal of how to monitor uh, in real time the tumor temperature. So this is what we call magneto-nanothermometry. So the same nanoparticle you were using to provide magnetic hyperthermia. Also, you can extract a signal, and this signal, the susceptibility signal of the sample, can be used as a local temperature sensor. So, and then you can do this in the real time. And it is very important to remember that the magnetic nanoparticles are distributed over the tumor. So you are sensing, you are mapping the temperature of the whole tumor. And the accuracy of this approach is very, very uh, uh, applicable in the system. So we have accuracy of better than zero point 0.1 Celsius, which is extremely important for controlling the magnetic hyperthermia process. So let's move for the second possibility of controlling, which is the morphology. If you go to the literature, you will see magnet nanoparticles presenting typical spherical nanoparticles, most of them spherical nanoparticles, regardless the phase. But also there are some morphology which is not exactly spherical, like this one, cubic, very interesting cubic morphology. So, of course, both morphology can be used to perform magnetic hyperthermia. But there is a very exotic magnetic morphology we call nano ring. So here you can see a TM picture of typical nano ring, which has an internal diameter and external diameter. In this case, we managed to synthesize magnetite nanorings, and you can see typically internal diameter of this sample around 40 nanometer, external diameter around 80 nanometer. So here is in the lower part of my slide is typical TM picture. So what are the interesting aspects of magnetic nanorings? So in magnetic nanorings, what you have, it's a sort of spin vortex. So the spins are oriented along the ring in such a way that this magnet nanoparticles, it doesn't show a magnetic moment out of the plane of the ring. So, and then it leads to very interesting features. So the first point is that the system uh, shows a sort of spin vortex, and at the same time, although there is no net magnetization out of the plane of the nanorings, the hysteresis of this material is indeed opening. The cycle is open, as you can see here on the left hand side in the lower part. So this is the hysteresis, and the area you can see above and below the zero applied field. So that area actually scales the heat dissipation of this material. What are the interesting outcomes of this morphology? First, because you don't have a magnetic moment of the nanoparticles out of the plane of the nanorings, you have a minimization of magnetic dipole interaction. So it means this kind of morphology prevents agglomeration of magnetic nanoparticles, which is a very important aspect. Once nanoparticles agglomerate, the response of these agglomerate nanoparticles to AC magnetic field, it changes. So the heating dissipation depends on the sample's agglomeration. And this kind of morphology just prevents agglomeration. And at the same time, there is a strong interaction between the applied AC field and the magnetic system and the spin system in nanorings. Okay, let's see how these nanorings perform in a typical magnetic hyperthermia experiment. So we did this experiment using phantom actually. On the right hand side, you can see how the phantom temperature goes with the time for application of AC field. So we kept the frequency constant at 330 kilohertz, and then we change the amplitude of AC field. You can see that for the lower end of the amplitude of AC field, which is 100 Hertz, you can see a very, very small heat dissipation down here. But if you move to 150 Hertz, now you can see this dissipation, and which is very important, very quickly the system reach the saturation or the operation temperature. However, we want to control the system in a way that the asymptotic temperature can stay between 40 and 45 C. And if you see the application of 200 Hz amplitude of AC field, the saturation goes roughly around 40. And for 240 Hz, you can see the saturation going around 46, which means you can modulate the amplitude of the AC field between 200 Hz and 240 Hz to meet the precise temperature that you need to make thermal sensitization of the cancer cells. So this is a way to combine both the morphology of the magnetic nanoparticle and your instrumentation. So combination of both using this kind of exotic morphology, you can meet the best situation to perform magnetic hyperthermia in terms of cancer treatment. So the main conclusions of my presentation I want to show you is that first, it is possible to control the magnetic hyperthermia and preset the operating temperature. So the second important point is that once you can control the operating temperature, you can write down operating protocols which are clinically safe. So that is a very important step to bring in magnetic hyperthermia as a usable therapy uh, to be available for the oncology area. And the third point is that magnetic nanoring is a very, very promising morphology to perform magnetic hyperthermia as a clinically safe therapy. And the fourth point is that you can, of course, you can manage it to control the frequency and the amplitude of the applied AC field. And then the combination of morphology and the and the setting of the frequency and amplitude of the AC field. So this combination is extremely important and possible to bring the magnetic hyperthermia to a clinically safe stage. So I would like to thank all of you and the organizers of this meeting. Thank you so much. So if you want to take any question, I'm here available to you. Thank you.
Thank you, Dr. Polo, for your wonderful presentation. Does anyone have any query? Hope there are no queries.
Okay.
Thank thank you. Thank you, Dr. Polo, for your wonderful presentation.
Thank you. Thank you, and have a
Thank
good day.
you. Thank you. Okay, let's move on to the next presentation. Is an oral presentation by Dr. Elves out there from the University of Fax Tunisia. Hello, Dr. Elves. Are you ready with your presentation? Hello, Dr. Elvis. Are you ready with your presentation? Okay, let's move on to the next presentation. The next presentation is by Dr. Amrita Bharati Mishra from Vellore Institute of Technology, India. Hello, Dr. Amrita. Are you ready with your presentation?
Yes, yes, I'm ready.
Okay, I'm making you the presenter now. Yes, I made you the presenter. Please click on the share button to share your screen.
Okay. Is it visible?
Yes, your screen is visible. Please make it a full screen.
Okay. Okay,
Yeah,
so
that's
hello
perfect.
everybody.
That's perfect.
Okay. Hello everyone. I'm Amrita Bharati Mishra. I'm a PhD research scholar in Vellore Institute of Technology, India. And the topic of my talk is bio-inspired artificial synapse based on carbon quantum dots dispersed in indigo molecular layer for neuromorphic applications. So before going to our topic, I'll just let you know that I belong, like our university is at Vellore, which is 2,196 kilometer away from New Delhi, which is the capital of India. And our university has a very beautiful green campus spread over an area of 372 acres. So now let me go to my topic. So we can see that there is a number of devices that has emerged under the umbrella of internet of things. So we have these devices connected to the internet or the cloud, and in a way they are interconnected to each other. So in case of any malicious hacker gets access to any of the device, he can actually get access to the cloud and to other devices also. So instead of securing the cloud, it is better to install hardware security primitives in each of these devices. So there are about more than 25 billion devices that are connected to the internet and to each other. If we look at the economy, it is at least 7.1 trillion US dollars, which is even more than the GDP of India itself. So there is a big amount of data that is flowing across the universe, like 44 zettabyte or 44 trillion gigabytes of data is flowing per second. This huge data that has emerged, people call it as big data. And this asynchronous data comes from all the sources like personalized healthcare, a lot of education applications, telecommunications, e-com like Amazon and all. So for that, there is an urgent need of high density and low cost memory devices. And also another thing is that the emergence of artificial intelligence. Artificial intelligence has got significant applications in the field of health, autonomous vehicles, manufacturing, entertainment. So even we are using this artificial intelligence in our day-to-day life, like Alexa, Siri, Google Assistant, like OK Google, and camera filters in Snapchats, etc. So this AI is now everywhere. And to accelerate the AI applications, we need dedicated processors other than the conventional CPUs and GPUs because they are neither that much energy efficient or area efficient. So till now, in-memory computing processors have been developed which can handle the AI applications more efficiently. It has about 10 to the power 6 times better energy efficiency than the conventional CPUs and GPUs, but still in-memory computing is inferior than the human brain. So we should, so there is an need for designing the computer systems that are based on the human brain. So why should we consider brain as our model system? Because brain is profoundly compact with parallel computation and 3D organization. It has self-learning abilities which can adapt to different environmental changes. It has decision-making capabilities, and it can host co-location of logic and memory. But the conventional computers are normally based on the von Neumann architecture, where the CPU and the memory are located at two different locations. So when the data flows between the CPU and the memory, there is a lot of power consumptions. Whereas in neuromorphic architecture, the neurons and synapses are used for both processing and memory. And in von Neumann architecture, it uses only binary input and gives out binary output, whereas in neuromorphic architecture they have spiking neural networks. And von Neumann architecture is clock driven, or it has synchronous data, whereas neuromorphic architecture is event driven and it has asynchronous data. So why we are going towards the neuromorphic kind of computing architecture? So the term actually neuromorphic was originally coined in 1990s by Carver Mead. Neuromorphic kind of computing might provide very much low power, nearly because it is modeled after human brain, and a human brain only consumes up to 20 watt of power, and it has high scalability, high fault tolerance, and it is robust to variability. It is also program free, means once it takes the data, it can train by itself, and so it has unsupervised learning capability, and it is highly adaptable, and reconfigurability is also there. That means the conductance change can occur even when the program is running. And since human brain is most efficient machine, so there are a lot of attempts that has been taken to simulate the brain. IBM has used their blue gene supercomputers to simulate 1% of the brain. For simulating 4.5% of the human brain also, we need at least 1 megawatt of power. And another significant property is the massive parallelism in the human brain. That is, all the neurons are working at the same time, which makes the overall process so energy efficient. So, if you want to process these widely parallel kind of systems or neural networks on your digital computers, then high bandwidth is required to transmit spikes to and fro between memory and processor. So, what we can conclude is the true potential of this bio inspired learning rules can be realized only if we implement them on a compatible hardware, which can make these learning rules one on one with the algorithm on the hardware. So, we need to make hardware which can replicate or which can mimic the neurons and synapse and the learning algorithm or the learning rules. The neuromorphic kind of computing has got lot of applications like pattern classification, machine vision, pattern extraction, robotics, etc. So before I go ahead to tell about how these neurons, how we are going to mimic the neurons into hardware, let us understand some basic structure of the biological neuron. So a neuron has three parts. The middle body is called soma, and the branched part is called dendrites. And the action through which the spikes or the axon potential is carried out to another neuron, and this portion is called as the so there are actually 10 to the power 11 neurons in a human cerebral cortex, and each of these neurons are kind of connected to, let's say, 10 to the power 3 or 10 to the power 4 other neurons with the help of this synapse. The synapse are the elements which connect two neurons. So this is kind of neural network like organization that is present in the human brain with 10 to the power 11 neurons, and 10 to the power 11 neurons and like 10 to the power 15 synapses, and the overall intelligence of any organism depends on the number of neurons and how they are connected. So let's compare for different organisms. Trichoplax does not have any neuron and does not have any synapse, so it's kind of most unintelligent organisms. So as we go down this ladder, we go to roundworm, honeybee, mouse, cat, and finally we reach human brain. We can see the number of neurons and the number of synapses are increasing, and correspondingly we see that the sense of hearing, the quality of smelling, quality of intelligence overall is also increases when it comes to the human brain. Um, so in the synapse, actually the transmission can happen like electrical signal or chemical signal. Um, I'll explain a bit more about the synapse. This is the image of synapse. It acts as a communication channel between the neurons. So the neurons which is receiving the information or the spike train may be in the form of electrical signal or optical signal or any other kind of stimuli is called the presynaptic neuron, and the other neuron which receives the information or this axon potential is called postsynaptic neuron. So the transmission of the axon potential can be electrical, which is very fast, and it can be chemical, which is actually slow. The transmission delay is close to 0.2 milliseconds, like in electrical, whereas in chemical it is close to 2 millisecond. So our defensive reflexes, which needs to act very fast, are mostly dependent upon this electrical kind of transmission mechanism. Whereas our chemical mechanisms are kind of more responsible for the sense of thoughts, which are mostly present within our central nervous system and are mostly responsible for thoughts. Um, so let's talk about. Give an idea about the synaptic plasticity in the learning. Actually, the strength of the synapse is determined by the intensity change in the postsynaptic potential. So, if this is the presynapse and this is the postsynapse, we are giving voltage spikes here, and we can detect the change in conductance or the current in the postsynaptic postsynaptic membrane. So exactly, synaptic plasticity is the ability of our synapse to change its strength in response to the neural stimuli. This stimuli not only depends on the presynaptic neuron, but is also it depends on the difference between the spiking pattern also of the postsynaptic neuron. So if the synapse kind of increases in strength, like it increases in strength because of the neurological stimuli, then it's called synaptic potentiation. Whereas if it kind of decreases, it's called as a synaptic depression. Now this kind of synaptic plasticity behavior or these changes can be short term or it can be long term. Short term actually lasts for like some seconds or minutes, or and if it is long term, then the plasticity then can range from like hours to days to years. Mostly long term potentiation is responsible for all the learning and memory that we have for our whole intelligence, and it is a kind of dependent on the long term synaptic plasticity. So if the strength of this synapse we had to remain constant, if this strength has to remain the same, then we will not learn anything at all. So it's only because of the ability to change the strength of the synapse that we learn new things. That's why it's actually truly called like practice makes a man perfect. Only if we practice it or we there is increase in the synaptic plasticity, then only we learn a thing. um, so there are a lot of devices that are emerging for neuromorphic computing applications, like because the traditional CMOS semiconductors hardware can not emulate the brain. um, is not They cannot actually emulate the brain. So we have taken different approaches to make emerging devices which can work with lesser power consumption and with better speed. Mm, so the artificial synapse can be actually categorized into two terminal and three terminal devices. Two terminal devices are such as memristors, ferroelectric tunnel junctions, and this phase change memories. Also, there are three terminal devices, mostly the transistors, ferroelectric transistors, charge trapping transistors, and they have been researched at the artificial synapse. Even we can use optical devices also. So, out of all these various types of memory devices, we are working on two terminal memristors because it has several benefits that I will discuss in the next slides. So, now let me give a brief idea about this discovery. So, memristors was first postulated in 1971 by Professor Leon Chua. So memristors is considered as the fourth fundamental passive elements circuit element, following the resistor, capacitor, and inductor. In 2018, a team of researchers at Packard Labs led by Stanley Williams connected the concept of memristors to the physical devices. So by definition, we can describe a memristor as an electrical component, actually which controls the flow of electrical current in a circuit. It also remembers the amount of charge that has previously flowed through it. They are important because they can retain memory without power. So they are considered as a promising for synaptic applications, and they can combine memory and resistance through voltage induced changes. There are different types of memristors. PRAM, or the parallel resistive access memories, which uses crystallinity changes for resistance. There are also some other kind of memristors. We are mostly working on ReRAM, that is resistive random access memory, which utilizes analog resistance shifts, and it has some other benefits also, like memristors can be has integration density that is comparable to DRAM, non-volatility similar to flash memory, fast read speed close to SRAM, minimal standby power requirements. So they are actually good for AI advancement and processing data with low power. So the two terminal memristors. So this is what is actually we are doing in our lab scale is we are just mimicking the functioning of a biological synapse by making an artificial synaptic device. The device that we are using is two terminal device because it has simple device structures and can have superior scalability, large on and off ratio, analog from memory, and also it consumes very low power, and it shows synapse like properties. So if we talk in terms of structure also, this is the structure of a memristor. So a memristor is a very simple two-terminal device structures where the active material is sandwiched between two metal electrodes, which is somewhat similar to the presynaptic neuron, synapse, and postsynaptic neuron structures. So in the memristors, the conductance of the active material can be changed by applying voltage. This conductance modulations can be actually used to emulate the synaptic weight update characteristics. Um, the memristors are operated through conductance change, which is originated from the formation of this conductive filament paths or modulations of oxygen vacancies. The conductance change from the high resistance state HRS to the low resistance state LRS is called as set process, and the LRS to HRS state is called as reset state. This conductance change behaviors of memristors depends on the type of materials, operations, and mechanism and device structures. So I'll talk about the types of measurements that we perform. The first one is the resistive switching memory switching measurements to confirm that if our device has memory characteristics. First, we plot the IV, take the IV measurements, current voltage, and see what is the set and reset voltage. Then also we perform measure to perform like retention and endurance measurement, where in retention the resistance is plotted across the time, and in endurance the resistance change is plotted across cycles, and we see how much stable is our low resistance state and high resistance state from each other. So once we confirm the memory measure from the memory measurements, then we go for the neuromorphic measurements. um, we perform the pulsed measurements, in which we give voltage spikes either in the form of electrical voltage pulses or optical light intensity pulses. Then we get current spikes from the as output, or the conductance change as the output. If our current is increasing when we are giving the voltage spike, if it is increasing or the conductance change is more, it is increasing, then we tell that our device is learning. And if we give the voltage spike of opposite polarity and see that the current is gradually decreasing, we tell it that the device is forgetting. Similarly, we can perform the learning experiment again and see that if the device is again relearning whatever it has forgotten. From these curves, we can see that these curves can be fitted exponentially, but in our device, what we expect is the memorization should be linear. So to see how much is the deviation from the linearity, we plot this non-linearity factor curve. Like for example, then we calculate like how much is that factor out of 1. So lesser the non-linear factor, better is our device. So how to choose the materials for neuromorphic computings? So different nanomaterials have been already studied for the neuromorphic applications. Memristors for neuromorphic applications like metal oxides, like titanium dioxide and all. And in case of organics like polymers and bio-inspired nanocellulose and all. In 2D materials also, graphene, MOS2, WSC2 has already been studied, and QDs, emerging materials like QD perovskites. But we are mostly interested in the organic materials because they are flexible. They can be obtained in a very low cost, provides biocompatibility. It gives analogous and continuous operation, and it has versatile device architecture. So now I will go on to the work that we have performed. This is kind of biological synapse, and we have tried to mimic it using our artificial synaptic devices. So the materials that we have used are carbon quantum dots that are dispersed in indigo molecular layer. We have taken carbon quantum dots because it has good optical sensitivity, high fluorescence, excellent electrical conductivity. Also, a QD film. If we make a film, thin film out of QDs, they will provide very nice uniformity, scalability. They have photo switching property also, and they can provide flexibility. So they are a very good potential candidate for being used for memory applications. And Indigo has been well established for memristive application, but our group is the first to introduce Indigo for neuromorphic computing applications. The best part of Indigo molecule is that it has M bipolar nature. That means it has same number of electrons and holes. So because of that, it has promising charge transport characteristics like high mobility. It provides good stability against degradation, and it has can work in low operating voltages. It has already also been used for applications, like it has got its applications in photodetectors, organic photovoltaics, FETs, singlet fission, organic lasers, and all. So we have synthesized the carbon quantum dots from jaggery with a very easy thermal decomposition method. We annealed the jaggery at 200 degree, 220 and 240 degrees. And then the obtained material, we grounded it using a mortar and pestle, and then uh, we dissolved it in a put it in a solvent, ultrasonicated it for some times, and then after centrifugation and filtration, this is how it looks under the optical light. And when we put it in under UV light, we are getting green fluorescent emission. So to confirm if we have obtained the QDs, we perform the transmission electron microscopy. And for 40-degree sample and 200-degree QDs, we are getting lattice fringes separated by 0.288 nanometer and 0.16 nanometer. And from the size distribution curve, we confirm that the QDs are of size 3.5 to 4 nanometer. And these are the UV top plot, which says that with increasing the annealing temperature, the optical band gap of the QDs have also gradually increased. And we have also performed the PL spectroscopy, and to confirm, and for indigo we have performed the FTIR measurements spectroscopy. So this is how it is, the schematic diagram of our device. We have two terminal platinum carbon QDs plus indigo platinum device. This is the electrode, and we have spin coated our material. These electrodes are separated, have a gap of 10 micrometers. And first we performed the IV measurements to IV measurements. These are like 25 cycles of repetitions. We can see that we are getting negative differential resistance in the IV curve, and our device is showing analog switching, which is desirable for neuromorphic computing. And for the studying the conduction mechanism of the device, we have plotted the current voltage curve and divided it into 5 regions where different conduction mechanisms prevail. The first region is this one, where the conduction is due to thermionic emission. The second portion is definitely the NDR, negative differential resistance. And third one corresponds to the ohmic conduction, because we are getting slope of 1 for log I versus log V graph. Then in case of region 4, first we are getting space charge limited conduction, but when we are going on increasing the voltage, so now what is happening is more charge carriers are getting in the trap defect that is present in indigo molecular layer. So we are getting charge trap limited conduction. And then on further increasing the voltage, we are getting tunneling, and then for voltage more than 1.82 electron volt, we are getting field emission. Then we have performed the read write erase cycle measurements to learn about the memory characteristics. We have read the device at 1 volt. We have write it is 5 volt and erased it minus 5 volt, and we are getting a stable HRS and LRS state for 1500 cycles, which resistance change of 36.3 mega ohms. Then we have done the neuromorphic measurements on our two terminal devices. This is the pulse that we have given. We have the read voltage was 2 volt, and for negative minus 2.1, for minus 2.5 volt, actually we are getting potentiation, and for positive pulse voltage of 0.25 volt, we are getting depression. In one cycle of potentiation and depression, actually we have given 20 pulses for potentiation and 20 pulses for depression. And we have fitted this potentiation in depression using double exponential function. So we have plotted the long-term potentiation and long-term depression curves by varying the pulse voltage first and keeping the read voltage constant. And when we see that the non-linearity factor for all the different pulse voltages are nearly same, 0.75. So as I told before, we want our device to be more linear, to show the potentiation and depression curves should be more linear. So for that we tried to change the parameters, like we changed kept the pulse voltage constant for this time and varied the read voltage. Still we got a non-linearity factor of 0.7. So for the next time what we did was we varied the pulse width. Pulse widths mean the duration between the duration of a pulse. So when we decrease the pulse width, we saw that the nonlinearity factor has now gradually decreased to 0.57. And um, here you have just performed the like 8 cycles of potentiation and depression and 10 cycles of potentiation and depression. When we are trying to see the change in the postsynaptic current versus the potentiation or depression cycles, we are seeing that this curve is linearly increasing. This is linearly increasing up to 8 cycles, but after that it is kind of saturating. So since this is an organic material, mm, so the response is a bit slow. Maybe you cannot tell slow, but mm, when you're using something very raw material that is extracted plant extract, and we have not, but the ease of synthesis is telling that if we make a very like device, vertical kind of devices or something, then actually we can also increase the response even better, and without this is without any toxicity. Biocompatibility is a very good factor for that. Can actually use these kind of devices for future use, where we can avoid the toxic inorganic components or the inorganic semiconducting materials. So with this, I conclude my topic. So we have reported an extremely stable neuromorphic device showing long-term potentiation and long-term depression. And the carbon quantum dots are synthesized via simple route using edible jaggery. And the ease of synthesis of the room temperature stable carbon quantum dots using these edible sources provides a very good advantage for the application. And also we see that the because of the uniform distribution of the carbon quantum dots, it stabilizes the resistive switching device. The two terminal device showed not only memory functions but also excellent learning and forgetting characteristics that are essential for realizing the artificial synapse for neuromorphic computation working at room temperature. So room temperature working is also a advantage of this device. And our read write erase cycle also showed excellent high resistance and low resistance state stability for more than like 1500 cycles. So these kind of molecular based systems for such application attracts more attention because of its ease of fabrications and room temperature operations. um, so these are some references that I have used. And this is my group, my guide, Dr. Ramesh Thamankar. And for knowing more about our work, you can follow us at neosmatlab.com. Thank you.
Thank you, Dr. Amrita, for your wonderful presentation. Does anyone have any query?
Hello, Amrita.
Yeah, hello, sir.
Thank you for your presentation. I have just a quick query.
Okay.
So you have used carbon dots for
Yes.
your purpose, and you
Yes.
have used different temperature to
Yes.
for the carbonization.
Yeah.
And what is the differences of uh, varying those temperatures? I mean, there are
Sir,
any kind of
actually, yeah. Okay. So actually, the idea was when we increase the annealing temperature, the size of the quantum dots decreases. So as it decreases, the band gap, optical band gap changes, and we wanted some different kind of emissions. But after varying it like 200, 220, and 240, we saw that all the three solutions were showing same green fluorescent color. So we did not work with all three of them for the device fabrication and all. We just took the 200 one because all of them were showing the same green emission. But in future, our plan is to make quantum dots of different colors like green,
okay.
blue. That's why we varied the temperature.
Okay, okay. Actually, yeah, that's true. That actually, with changing temperature, that will not change the size of the quantum dots actually they help crystallization actually.
Yeah,
So
maybe
yeah,
some,
that's why I ask you this question.
yeah,
Okay.
maybe some functional groups has to be changed in order to change the
Yes,
color.
yes, little bit. Yes. Okay, okay.
So
Okay. Thank you.
thank you.
I hope there are no more questions. Let's move. Thank you once again, Dr. Amrita Bharati, for your wonderful presentation.
Thank you.
Thank you. Let's move on to the next presentation. The next presentation is by Dr. Elvez Aute from the University of Fax, Tunisia. Hello, Dr. Elvez. Are you ready with your presentation? Okay, let's move on to the next presentation. The next presentation is by Dr. Khadija Bakholda from the University of Sfax, Tunisia. Hello, Dr. Khadija. Are you ready with your presentation?
Yes, hello, doctor.
Hi, are you ready with your presentation?
Yes, okay.
Okay, I'm making you the presenter. Please click on the share button to share your screen.
Okay, that's do you see the slide?
Yes, yes, your screen is visible. Please make it a full screen. Kindly click on the slideshow option.
Slideshow option.
Yeah, the bottom right corner, the fourth icon. The fourth icon.
The diaporama, the slideshow.
Yes, yes.
I make it.
But it's not happening. Okay, Dr. Khadija, stop share the screen and follow my instructions.
Okay.
Yeah, now click on the share button. After that, you will get a pop-up window where you have to choose the entire screen option.
Yes.
Yes, you have to select the entire screen option and give access to the audio.
Okay, screen action.
Yes, now make it a full screen. Yes, your screen is visible. Please make it a full screen.
This full screen.
Yes, yes, the slideshow option. Please click on the slideshow option.
Yes. I
No,
click.
your screen is not visible. I think you have stopped shared your screen. Kindly click on the share button again and share your screen, please. Yes, now open your Yes, your screen is visible. Kindly open your PPT. Click on your PPT. Yes. Yes. Kindly click on the slideshow option now. Yeah, that's perfect. Yeah, kindly click on the slideshow option again. Yeah, that's perfect. Kindly continue with your presentation. Hello. Hello, Dr. Khadija. You're not audible. Kindly check your microphone settings. Your screen is visible, but you're not audible. Kindly check with your microphone settings. Your screen is perfect, Dr. Khadija. Kindly check your microphone settings. Kindly unmute yourself. Hello, Dr. Khadija. Sorry for the interruption. Kindly unmute yourself.
Mhm. It's okay
Yeah,
now?
now, yes, now you're audible. Yeah, make it a full screen. Yeah, that's perfect.
Okay, so now I can start?
Yes, yes. Yes, you can start now.
Okay, first, thank you so much for this opportunity. My name is Khadija Boukhulda. I am a postdoc from the University of Sfax, Tunisia, at the Laboratory of Toxicology, Microbiology, Environmental and Health. Today, I will present a project about toxicity assessment on hematology, biochemical, and histopathological alteration of cobalt nanoparticle exposed subactineously to aged rats. So today, nanotechnology have revolutionized the world and invaded various fields, providing nanomaterials. These nanomaterials are defined as materials of which a single unit is sized between 100 nanometers. And there are two types of nanomaterials. Nano-object, which include a nanoparticle, nanofiber, and nanosheet, and nanostructured materials, which include aggregates and agglomerates, nanocomposite, and nanoporous materials. The nanoparticles are classified into organic nanoparticles such as the boson and the carbon-based nanoparticle, and inorganic such as quantum dot and metal oxide nanoparticle. These nanoparticles are characterized by specific physiochemical properties such as their tendency to agglomerate and aggregate, their reactivity or load, and their shape and size. Okay, so today in this presentation, we investigated the toxicity effect of cobalt nanoparticle. These nanoparticles are inorganic and metallic, and they are used as biomedical sensor, pigment and dyes, and contrast agent in medical imaging. But although there are beneficial effects, nanoparticles can also have toxic effect as their accumulation in waste, soil, water, and the atmosphere, and they can enter the body by various routes, including oral, respiratory, and cutaneous, and translocated to the organ via the bloodstream. Their toxic effect could lead to the appearance of a number of diseases in the heart, liver, kidney, brain, and blood in the adult, but their toxicity in the aged until now is unclear. That's why our aim is therefore to assess the toxicity of cobalt nanoparticles in aged rats by studying their effects on hematological and biochemical parameters, and also to studying the genotoxicity and oxidative stress in erythrocyte. Moving now to the result. The result of characterization of the cobalt nanoparticle showed a cubic spinel crystalline structure and broad peaks, indicating the small size of these crystalline, which facilitate their penetration in the body. Similarly, the Raman showed the presence of four active modes and the strong absorption between 120 and 613 nanometers. Also, the scan electron microscopy shows an ultra-thin semispheric form of our sample, and the ADX show a uniform distribution of oxygen and cobalt in cobalt nanoparticle. The analysis of hematological parameters show that subactinous exposure to cobalt nanoparticle demonstrate a reduction in the red blood cells and hematocrit accompanied by a significant decrease in hemoglobin concentration and mean corpuscular volume only for the high doses, that's mean 4 milligram per kilogram, and an increase in the plates. This alteration may indicate the toxic effect of cobalt nanoparticle in the secretion of erythropoietin, which stimulates the production of red blood cells and the synthesis of hemoglobin during the maturation of red blood cells. Just a minute. The microscopic observation of blood smear showed normal numbers of red blood cells, lymphocytes, and platelets in the control group. But exposure to a cobalt nanoparticle caused membrane damage dose-dependent in red blood cells and the appearance of platelet aggregation. Now, concerning the effect of cobalt nanoparticle on cellular reactive oxygen space and production, the result of this test showed that cobalt nanoparticle induces a dose-dependent excess production of reactive oxygen species marked by green fluorescence, and the appearance of these species exceed 25 percent for the treated group. With regard to the assay of pro-oxidant and antioxidant markers for the oxidative stress, the results show that cobalt nanoparticle induce a significant decrease in the enzyme that's, for example, the glutathione peroxidase, the superoxide dismutase, and the catalase. And a significant increase in the level of malondialdehyde, the final product of protein oxidation, and also a significant increase in the nitric oxide. Moving now to the effect of nanoparticle for the genotoxic effect, our results show a normal appearance of erythrocyte in aged control rats, but a significant increase in the frequency of nucleated erythrocyte for the treated group. That means cobalt nanoparticle induces a dose-dependent genotoxic effect. Thank you for your attention.
Thank you, Dr. Khadija, for your wonderful presentation. Does anyone have any queries?
Thank you. Do you have any question?
Hope there are no questions. Thank you once again, Dr. Khadija, for your wonderful presentation.
Thank
The next
you.
Thank you. The next presentation is by Dr. Yes, let's move on to the next presentation. The next presentation is by Dr. Elvez Abdef from the University of Fax from Tunisia. Hello, Dr. Elvez. Are you ready with your presentation? Okay, let's move on to the next presentation. The next presentation is by Dr. Deepti Mandinda from the Catalan Institute of Nanoscience and Nanotechnology, Spain. Hello, Dr. Deepti Man. Are you ready with your presentation?
Yes, yes. Hello. I am ready with my
Yeah.
presentation.
Okay, I'm making you the presenter. Kindly click on the. Wait a minute. Yes, I'm making you the presenter. Kindly click on the share button to share your screen.
Okay.
Yes, your screen is visible. Kindly make it a full screen
Okay. Yes, sure.
and start your presentation.
Is it full screen now?
No, not yet.
Just a moment. So is it okay?
Yes, that's perfect. Kindly go ahead with your presentation.
Okay, thank you. So, hello everyone. I am Dipti Mandinda. I am working in ICN2 Barcelona as a senior postdoctoral researcher. Today, I'm going to present my research works, which is based on visible light active graphene-based nanomaterials for solar hydrogen production. So this is the synopsis of my presentation, why we need hydrogen as the fuel and how about its production in presence of solar light and which type of catalyst we have used so far for this purpose. Now how we can utilize graphene based materials for this purpose, and then we will present dye sensitization techniques and also my result and discussions and finally conclusions. So first I will start with why we need renewable fuels. So if you look into the recent chart of consumed fuels, so you can see most of the fuels are coming from the renewable energy sources and very few from the renewable energy sources. And the most concerning among it that almost 80% of the fossil fuels has been consumed by us so far. So we must have to look for a new renewable energy sources. And if you have a closely look into the renewable energy sources, you can see mainly it consists of six sources, kind of solar, wind, hydroelectric, biomass, and hydrogen energy. So we are more interested about this hydrogen energy, although the percentage currently used is very less, but we are more interested into it as it has several factors. As it is zero carbon fuel, it has the highest energy density among all the fossil fuels, and it can be stored, transported and delivered. It can be used in different industries as well as for different vehicles and fuel cells. So with these excellent properties, it has the potentiality for the next generation renewable fuels. So if we look into the current scenario of its production, then mainly hydrogen is coming from the natural sources, that is gas, coal or oil. Only 4% of the hydrogen is coming from the electrolysis of water. And if you consider solar water splitting, then its percentage is more or less. So as we are more wanted to make it economical, so we are focusing on solar water splitting reactions. It's mainly consists of two half reactions, that is hydrogen evolution reaction and another is oxygen evolution reaction. And for this, the energy difference will be 1.23 electron volt. So as we are here more focusing on the production of hydrogen, so we will consider the half reaction, that is hydrogen evolution reaction. And for these hydrogen evolution reactions, we have to design a semiconductor which band gap should be more than 1.23 electron volt but less than 3 electron volt for the effective use of the solar light. And we also have the conduction band of semiconductor which has more negative potential compared to the hydrogen energy. And we have a suitable sacrificial electron donor like triethanolamine or ascorbic acid to scavenge holes. So now if we look into the literature, so far different type of photocatalyst has been explored for this purpose. First, scientists have used transition metal oxide, sulfide on nitride beds wide bandgap semiconductor with the help of using co-catalyst. But they also face different problems. Mainly, they are active in the UV light, so they can only absorb 4% of the solar spectrum. So to increase their efficiency, we have to tune their band gap. So in next generation, scientists have tried to tune their band gaps by doping different metal or non-metal ions or using sensitizers to attach with those semiconductors that can absorb more visible light. But they also suffer different drawbacks like toxicity, corrosiveness, or instability. So nowadays, people are more interested about using this metal-free, that is carbon-based and nanomaterials as a photocatalyst for this purpose. So there are different types of carbon-based photocatalyst that consist of carbon nitride, graphene, carbon nanotube, or carbon dots. But my focus will be on developing this graphene-based photocatalyst. So the question will arise, why graphene? So we all know that graphene is a one atom thick sp2 hybridized carbon network, and it has different remarkable properties such as its aromatic macromolecular network helps to absorb solar light. It has tunable band gap from insulator to metal, and it has very high electrical conductivity. Its specific surface area is also quite high. It has excellent optical transmittance as well as it's very stable. So with these beautiful properties, it has the it has all the properties to work for a good photocatalyst. But the problem is its intrinsic zero band gap semiconductor behavior. So to utilize it as a photocatalyst, we have to open up its band gap, and it can be done by two ways. Either you can oxidize it to make graphene oxide, or you can cut its size to few nanometer quantum dots, and with these two techniques you can open up their band gap. So so far people also tried to explore those techniques, and in 2010 first paper coming out using graphene oxide nanosheets as a active photocatalyst, although their efficiency for hydrogen production was very low. Then also people have tried to dope different heteroatoms like phosphorus or sulfur in their structures to increase their efficiency. Not only that, people have also tried graphene quantum dots, also modified their structures, but they also suffers efficiency. So the question will arise, why they have such poor activity. So if you look into their absorption spectra, you can see both graphene oxide or graphene quantum dot both have absorption mainly in the UV region. So unless and until we tune their band structure or do some structural engineering to make them visible light active, we cannot increase their efficiency. And for this purpose, we have chosen dye sensitization technique. So we all know that in 1991, Professor Michael Gratzel first introduced different organic dyes to attach with semiconductor metal oxides, and they have utilized this kind of systems for the solar cell applications. So this is well-known dye-sensitized solar cells. And by inspiring with these techniques, actually, so we like to choose a suitable die which can be attached to the semiconductor, and then by choosing a suitable co-catalyst, we can increase this water reduction to make hydrogen. For this purpose, so I have develop some graphene quantum dot based systems, and we have attached some dyes covalently with those systems. So now the question will arise, why we choose graphene quantum dots apart from graphene oxide? Because these graphene quantum dots are the small graphene fragments which sized between 1 to 20 nanometer with exposed surface area. It has different carboxyl, hydroxyl or carbonyl groups on the edges as well as basal planes, and it has good biocompatibility and dispersibility, and it's very easier to functionalize its surfaces. So we have first synthesized these graphene quantum dots, and for this we have started from graphite powder. We have first oxidized using a modified Hammers method to make it micrometer size graphene oxide nanosheets, and then we cut their size to few nanometer quantum dots by using simple hydrothermal technique using sodium hydroxide as a base and heat treatment over 200 degrees. Then with those graphene quantum dots, we have covalently attached dye. Here we have used rhodamine dye on the edges of those graphene quantum dots by simple ADC-NHS coupling, making these amide linkages. And as a result of this amide linkage, now you can see we have increased the absorption of these quantum dots in the visible region. And then we have also characterized those materials with different microstructural analysis. You can see here from the TEM analysis, those bright spots are coming from these quantum dots, and they have sizes less than 5 nanometers. And also from the FTIR and XPS analysis, you can see that they have attached covalently with the graphene surfaces, and here especially this kind of amide linkages in the N1s deconvoluted spectra, and also these amide linkages in the FTR spectra confirms the covalent attachment of those rhodamine dyes on the surfaces of graphene quantum dots. And then we have explored those photocatalysts for hydrogen evolution reaction. And you can see here now it can produce hydrogen at a rate of 240 millimicromole per gram per hour without using any co-catalyst. That is, we do not require any platinum or palladium like of co-catalyst. Without co-catalyst, it can generate hydrogen under visible light irradiation. And the striking feature is that compared to the ionically attached systems, this kind of covalent attachment systems, you can see a large increment in their efficiency. So if you see their energy diagram, you can see first those rhodamine dyes absorb visible light, and electrons get excited from HOMO to LUMO, and those electrons are transferred to the conduction band of the graphene quantum dot by this covalent linkage, amide linkage. And here in this conduction band of graphene quantum dot, those excited electrons reduce water to make hydrogen. And if you go more detailed into their conductivity study, then you can see basically graphene quantum dot shows p type of semiconductor behavior because of presence of those carboxylic groups. Those are act as trap states in graphene quantum dots. But when we make these amide linkages to attach rhodamine dye on their surfaces, because of this amide linkage, actually those trap states are passivated, which makes this system as a NP type of semiconductor. You can see here, you can easily visible this kind of semiconductor behavior change by making this kind of covalent attachment. So this type of NP type of semiconductor is helping to delocalize this electron and hole separation, and also faster electron transfer from the LUMO of dye to the conduction band of graphene quantum dots. But the problem with this kind of system is the weak stability of rhodamine dye. So we all know that rhodamine dye degrades with time. So you can see here with increasing time, the activity of this catalyst is going down. So we have to improve their stability as well as their efficiency to make it as a powerful photocatalyst. So for this, in my next work, I have tried to modulate band gap of the graphene quantum dots. In this case, we have doped in situ during the synthesis of quantum dots, and we have doped nitrogen and sulfur during this hydrothermal technique. And as a result of it, you can see now this doped systems has more absorption in the visible region. And also we have tried to calculate the band gap, and you can see going from graphene quantum dot to the nitrogen and sulfur doped graphene quantum dot, their band gap decreases from 3.35 electron volt to 3.1 electron volt. So as a result of this kind of doping, it narrows the band gap, which increases their more visible light absorption, as well as it increases their conductivity. Then we have tried to measure their sizes through TM analysis, and you can see here and they are quite monodisperse, and the maximums and the size is around 3 nanometer. And we have also studied XPS analysis to confirm the presence of nitrogen and sulfur in the graphene quantum dot systems. And after these studies, we have to select a suitable dye which is stable for this photocatalytic purpose. And here we have chosen 2,3-diaminophenoxine. So the question will arise, why we choose this dye? Because it is a kind of electron-rich redox active molecule, and it has very stable conjugated planar structure, and it consists of donor acceptor type of structures. Actually, these donor acceptor structures will help to delocalize electron and holes, so that eventually separate those electrons holes effectively, and as a result of it, it will increase their photocatalytic activity. And then after this dye selection, we have attached covalently that dye with the doped graphene quantum dot systems, and as a result of it, you can see they have quite good visible light absorption. And we have also confirmed their covalent attachment by FTIR and XPS analysis. Here you can see amide linkages presence, and also from the deconvoluted spectra, these amide peaks are confirms that those dye are covalently attached with the doped graphene quantum dot systems. Then we have tried to utilize them as a active photocatalyst, and in this case you can see we have increased their catalytic activity a lot. Now they are showing activity more than 1.1 millimole per gram per hour compared to our previous material. And in all of these cases, it shows quite linear behavior with time. So that is very promising actually. And after their efficient photocatalytic behavior. We also tried to utilize as for long time. And in this case, we have studied their photocatalytic activity more than 50 hours. And you can see here, after 50 hours of continuous irradiation, it shows almost linear hydrogen production rate. So it confirms that it is quite stable in presence of visible light. And we also tried to calculate quantum yield with this material, and it shows a promising apparent quantum yield of 49% at 400 nanometer wavelength. So with this kind of material, so we have also studied their energy bandgap diagram and also conductivity. As I told, this kind of NP type of semiconductor behaviors helps to make them efficient charge separations to increase their efficiency. And another striking features with this material is it has a negative photocurrent response at zero bias voltage. So it can be a good candidate for photocathode materials for photoelectrochemical water splitting applications. So with this type of results, so we can now conclude that we have we have successfully synthesized 3 to 5 nanometer size quantum dots by cutting the micrometer size graphene oxide nanosheets, and we have tried to tune their band gap by doping heteroatoms, and we have covalently attached organic dyes to make them visible light active. And with these covalent linkages, actually they convert graphene quantum dots to NP type of semiconductor, which helps charge delocalization to increase their efficiency. Now it can produce hydrogen without using any co-catalyst, and it's a metal-free catalyst compared to previous metal-based semiconductors. And they are producing hydrogen at a reasonable hydrogen evolution rate, that is more than 1 millimole per gram per hour, and with better stability. So that's all from my presentation, and in acknowledgement, I like to acknowledge my previous supervisor, Professor Samal Kumar Shah from India, and Professor Soyoung Park from South Korea, and my current supervisor, Professor Daniel Ruiz, in this group. So finally, thank you for your kind attention, and also thanks to the organizers for giving me the chance to present my work in this conference. Thank you.
Thank you, Dr. Diptiman, for your wonderful presentation. Does anyone have any query? I hope there are no queries. Thank
Okay.
you once again, Dr. Diptiman Dinda, for your wonderful presentation.
Okay. Thank you. Thank you so much.
Thank you. Okay, let's move on to the next presentation. The next presentation is by Dr. Francesca Leonato from the University of Salento, Italy. Hello, Dr. Francesca. Are you ready with your presentation? Hello, Dr. Francesca. Are you ready with your presentation? Hello everyone. I think Dr. Francesca is not available at the moment. Okay, as per the schedule, let us take a lunch break. We'll get back to you after 30 minutes from now. So kindly stay connected. Thank you everyone.
This conference will now be recorded.
Hello everyone. I hope everyone is back for the afternoon session. Now let us begin our first session with the first talk. The first presentation is by Dr. Francesca Leonato from the University of Salento, Italy. Hello, Dr. Francesca. Are you ready with your presentation? Hello. Hello, everyone. Am I audible? Hello. Hello, everyone. Am I audible?
Yeah, audible. Audible.
Okay. Thank you. Thank you very much. So, hello. So, the first presentation is by Dr. Francesca Leonato from the University of Salento, Italy. Hello, Dr. Francesca. Are you ready with your presentation? Hello, Dr. Francesca. Are you ready with your presentation?
This conference will now be recorded.
Hello, Dr. Francesca. Are you ready with your presentation?
Yes, hello everybody. I
Okay.
try to share my screen.
Yeah, yeah. Yes, I'm giving the access from my end.
Okay, thank you very
Yes,
much.
yes. I made you the presenter. Please click on the share button to share your screen.
Okay, I'll try to share it.
Yes, your screen is visible. It's perfect.
Okay.
Please go ahead with your
Thank you.
presentation.
Thank you. Thank you. Hello, everybody. I am Francesca Leonetto from University of Salento in the south of Italy, and my presentation is on the reference nanoplastics for environmental studies, production and heat transfer modeling. So in this presentation, I will discuss about the risk for environment and human health brought about microplastics and nanoplastics and on the need of modern nanoplastics. So I will present some results of heat transfer study during polymer milling and production and characterization of PET nanoplastics relevant for biological studies. So the United Nations declared the plastic pollution of oceans as a planetary crisis because of the presence of marine litter, which is an persistent manufactured or processed solid material disposed or abandoned in the marine and coastal environment. More than 80% of marine litter is made of plastics, and those cause a lot of problems to the marine life, to the economy, climate, and, uh, and human health. These plastics, every year, 12 tons of plastics come into the environment, and the 94% of them accumulate on the seafloor, and the 1% is floating on the ocean surface, while the 5% come back to the beaches as beach litter. And we can talk about primary microplastics, which enter the ocean in the original microsites, or secondary microplastics, which result from the breakdown of larger plastics. Primary microplastics come from tires, from textiles, from marine coatings or other painting, for city dust, and so on, and several microplastics, secondary microplastics, have a very irregular form. So we can talk about mesoplastics, which have size higher than 5 millimeter, microplastics, which have size lower than 5 millimeter, and nanoplastics, when the size is lower than 1 micron. According to a well-defined agreement in the literature, also particles with size up to 1 microns are considered nanoplastics due to the difficulties of sampling in the ocean and separate the nanoplastic from the biofilm. And these micro and nanoplastics can be contaminated by different contaminants like polychlorinated biphenyls, bisphenol, polycyclic aromatic hydrocarbons, pesticide, perfluoroalkyls, pharmaceuticals, and metals. So there are several challenges connected with the topic of nanoplastics because we don't know how nanoplastics behave in natural system, and we don't know which is the environmental fate and impact of nanoplastics on living organisms and human health. So we need homogeneous and comparable data. We need a sampling and good analysis of microplastics and nanoplastics in the environment, and reliable assessment of exposure and biological effect, together with the remediation and recovery of nanoplastics from the environment. Therefore, the aim of my research is to avoid some drawback of the current research on nanoplastics, because many in vitro and in vivo studies are made using simplified nanoplastics and microplastics, which usually are monodispersed polystyrene and have spherical size, shape, but they are not representative of nanoplastics found in the environment. So we need an appropriate environmentally relevant nanoplastic suitable for studies on living organisms. And we need also suitable, fast, and low-cost production protocols. And we need also to understand the correlation between the viscoelastic properties of plastics and the processing parameter like time and temperature. And so we needed to understand the heat transport phenomena during the production on nanoplastic, model nanoplastic. In this research, we have focused on PET microplastics because PET represent 10% of global plastic production. Each year, 500 billion PET bottles are produced, but less than half are recycled. And PET has been used also as PET fibers, which account for 70% of all synthetic fibers. So the risk of pollution from PET, microplastics and microfibers is very high. In this research, we have produced PET nanoplastics from, at principle, we have produced microplastics starting from beach bottles collected in the beach in the Ionian Sea, or pellets, industrial pellets for production of bottle. And then from these microplastics, we have produced nanoplastics with fast and low-cost procedure, which enable to obtain polydispersed distribution. We have at first characterized these microplastics, and we have found that the microplastic obtained from beached bottles present very close size distribution to the microplastic obtained from pellet, and so on also a slight higher degree of crystallinity, but a higher specific surface area and lower circularity, because these microplastics have been aged in the environmental or marine environmental. The morphology is quite similar, but this microplastic present some rough and uneven surface and some microcracks. And these microcracks can enhance the uptake of pollutants, and so the risk of becoming polluted microplastics. Then the second part of the experimental activity has been devoted to the production of nanoplastic, starting from microplastic powder. So we have used high-speed mill with ball mill with zirconia ball, and we have produced these nanoplastics. And we have simulated also the heat transfer during nanoplastic production. The geometry is considered the jar of zirconia, which is in contact with a steel disc. And inside the jar, there is the mixture of zirconia ball, PET powders, and also water. And we have applied also some boundary conditions. So, for example, where the red line expresses external natural convection, the yellow line expresses the internal flux continuity, and the blue line, the violet line, the forced convection. Then the obtained nanoplastic have been also characterized by morphology, and we obtain polydispersed sites, irregular shapes, and irregular surfaces. For the simulation of heat transfer during nanoplastic production, we have used a heat balance where the term milling energy is have been expressed by the Brighton-Fires and Quade stress model as the product of the stress energy and the stress number. The stress energy is the average energy of the collisions, while the stress number, the average number of collisions per particle within a certain grinding time. So this energy of milling account for the elastic properties of grinding media, the milling ratio of the jar, the rotating field, and the progressive size reduction, which has an exponential decay. And so we have simulated the temperature evolution during milling and compared with the measurement experimentally achieved. So if we continuous mill for 1 hour the mixture of zirconia ball, polymer, and water, we can have an increase of about 10 degrees in the polymer temperature. And this is not good because we can become close if we continue to milling to the glass transition temperature of the particles, and so some aggregation or agglomeration of particles can occur. In fact, we have also measured the size distribution of the particles, and after 1 hour of milling, we have a very low quantity fraction of nanoparticles and a high fraction of microparticles. So the continuous milling is ineffective in producing nanoplastics. And for this reason, we have decided to process with milling and pause step. And so we have simulated the temperature evolution during milling. So we have milled for example 5 minutes, and we have stopped the mill for 5 minutes of pause, and we have changed these parameters, and we have arrived to the optimum, which is 2 minutes of milling and 5 minutes of pause. So after 10 cycles, so we have an increase of the temperature of only 2.5 degrees, and we reached a very distribution. These nanoparticles are also able to be fluorescent because they have some phenyl rings that experiment intramolecular interaction, and also there are intermolecular interaction between adjacent chains. And for this reason, they are able to emit also at excitation wavelengths higher than 410 nanometers. And these nanoparticles are also fluorescent under the green fluorescence and red fluorescence. For this reason, we have decided to test the ability of this nanoplastic to be used with some organism, and we choose bivalve mollusk because they behave as a bioindicator organism due to the high water filtration rate. For this reason, we have exposed the nanoplastic, the hemocytes of Mytilus galloprovincialis to nanoplastics, and we have seen that hemocytes exposed to nanoplastics experiment an internalization of the cell, which can be seen in this time-lapse video microscopy. We can see that the cells show a detectable change of their shape with the tendency to round and retract. And we have also observed a time-dependent increase of the number of internalizing cells, and also an increase of the fluorescence intensity inside the cells. To conclude, we have individuated a fast and reliable method to produce stable and reproducible water-dispersed nanometric PET in a short time. These PET nanoparticles are characterized by polydispersed sites, irregular shapes and surfaces, and autofluorescence. We have set a mathematical model able to characterize the heat transfer during wet ball milling of this thermoplastic polymer, and the model accounts for the elastic properties of the grinding media and for the elastic properties of the polymer, for the changing model geometry during the milling and pause steps, and for the temperature rise of the system in the milling jar. And then the produced nanoplastics have proved to be relevant for biological studies. So thank you for your kind attention.
Thank you, Dr. Francesco, for your wonderful presentation. Does anyone have any query? Hope there are no queries. Thank you once again, Dr. Francesco, for your wonderful presentation.
Thank you very much. Thank
Thank
you.
you. Thank you very much. Okay, let's move on to the next presentation. The next presentation is by Dr. Noor Jahan from Central University of Himachal Pradesh, India. Hello, Dr. Noor Jahan. Are you ready with your presentation?
Yes, ma'am. Good afternoon.
Yeah. Yeah, I'm
I'm
making you
Dr.
the
Noor.
presenter.
Okay,
Please click on the share button to share your screen.
okay,
Yeah, your screen is visible. Kindly make it a full screen and start your presentation.
okay, okay.
Yes, yes. Yes, your screen is visible. Kindly make it a full screen.
Uh,
Click on the slideshow option below. Yes, the fourth icon at the bottom. At the bottom right corner, you can find a slideshow option, the fourth icon, bottom right
yeah,
corner. Bottom right corner on your screen, you can find the slideshow. Bottom right corner.
is a pop-up,
No, not the
pop-out.
pop-up. No, not the pop-up. Kindly click on the slideshow option below. On your screen, you can find a slideshow option below. Yes, below. No, you have stop shared your screen, Dr. Nurjahan. Kindly click on the share button. Yeah,
Yeah,
yeah. Now click on the fourth icon at the bottom right corner. At the bottom, you can find the four icons, right? Kindly click on the slideshow option down at the bottom right corner. Yeah, that one. Yes, yes. Kindly click
this
on
one.
that. Yes. Yeah, that one. Slideshow option. Yes. Yeah, that's perfect. Kindly go ahead with your presentation.
Okay, good afternoon. I'm Dr. Noor Jahan, Assistant Professor in Central University of Himachal Pradesh. Now I'm presenting my work, Synthesis and Characterization of Polyaniline Decorated Iron-Based Magnetorheological Fluids. These fluids are the suspension of ferrous particles in carrier liquid, which are capable of changing the fluidic state to solid and like structure upon application of magnetic fluids. The outline of my talk, the introduction of magnetorheological fluids, application of MR fluids, challenging working with the MR fluid, promoting solution to overcome these challenges, and characterization performed, and then conclusion. MR fluids. MR fluids are micron-sized particle and soft iron particles. They disperse in different carrier medium depend on how many applications are used. Especially is the important characteristics of the MR fluids is the yield stress, viscosity, and settling rate, and which we varied the apply field is a show which saw as a behavior as a without field is a liquid fluid state like a Newtonian behavior. Then we apply a field, the fluid are showing a solid state like structures. The application of is a large, huge number of the application of MR fluids, the brakes, seats, cancer treatment, magnetic hypothermia, prosthetic legs, seismic protection of the fluids. The large number of application is like firstly for using a dampers. With dampers, we apply in Audi and it's a high The normal buses use a hydraulic buses. Then we now use for the MR fluid based dampers in buses. The all force are controlling these fluids and apply a field is automatically the damper work. And main challenging is a MR fluid is the settlement rate. It's a gravitational large is a large micron size particle and gravitational effect. Its agglomeration is very fast. The main cause of these fluids are settling rate is very fast. Proposing solution of challenging using composite of magnetic nanoparticle with enhanced magnetic property, introduce more polymers, elastomers, and use it different additives. They deal with these problems. We they introduce polyaniline conducting polymer. In this particular talk, we will discuss the effect of introduction of polyaniline on these rheological behaviors. Firstly, the synthesis of polyaniline. These additions of ammonia sulfate containing stirring and dark green precipitate after the filtrations and the heat at 80 degrees and they grinded the more to pastels. And these kind of fluids are shown. And then confirm the polyaniline is a short form of PANI and iron particle are used for MR fluids. Ensure the peak conformation is a 35 per peak 1 plane, and then also it's a polyaniline figure is showing a crystalline nature. And the FSM of the iron particles is a flake-like shaped particles, and SEMs also showing in the flower-like shapes. Preparation of the MR fluids. The MR powders in the 1 gram and silicon oil dispersed in 9 ml for 0% of the colloidal solution of the PANI. And then metals of the 0.98 gram of iron particle and zero point zero 0.02 gram of the polyaniline. These are conducting polymers. And then silicon oil, and then they add a 4.0.4%. The rheological behavior, the firstly for all the rheological is a flow and deformation of matter. And when we apply working on two modes, oscillation and rotation mode, and when we apply as such fluid without any field, as such fluid showing a Newtonian fluid. It's as viscosity like a constant honey-like structures, and showing a Newtonian fluid. When then we apply a field, the fluids is a chain-like structure. As such particles of iron particles and chain-like structure are formed, and then higher field is a saturate. This showing in saturation on at a higher field. Then we dope with a penny, and then as such fluids are not Newtonian, but it's showing a more concentration have we added of pani as such without field. It's a MR fluid are showing a non-Newtonian fluids. These are two kinds of fluids are Newtonian and non-Newtonian fluids. And Newtonian fluids we apply a force and no change in viscosity. But we non sorry Newtonian fluid we apply a force and no change in viscosity. But non-Newtonian fluids are apply a force and viscosity also increase and decrease also, and show that shear thinning behavior. And these fluids are share at the high share rate at 100 share rate. It's fluid are showing a shear thinning behavior. And then at the more concentration of the pani is a without field is also show as a non-Newtonian fluid. And this is a viscosity graphs, and the same like a behavior of viscosity as shear rest versus shear rate and the viscosity versus shear rate. It's as showing is a non and is a huge difference between without field and with field of the fluids. At the more concentration as the almost is a non-Newtonian fluid are shown. Then we add the sedimentation test also. It's a very fast sedimentation, but where disperse a penny fluid polymers is the settlement rate is a decreasing. Then it concludes the inclusion of polyaniline reduce the viscosity and yield stress, which is obvious due to the non-magnetic character of polyaniline. Sedimentation stability also enhance the polyaniline serve as the surface where the magnetic particle can reside. Due to conducting polymer nature, polymer these fluids can also behave as ER fluids and make range application of large number of application. Thank you.
Thank you, Dr. Nurjahan, for your wonderful presentation. Does anyone have any query? Hope there are no queries. Thank you once again, Dr. Nurjahan, for your wonderful presentation. And let's move on to the thank you. Let's move on to the next presentation. The next presentation is a poster presentation by Dr. Anita Iona Vishan from the National Institute for Laser, Plasma and Radiation Physics, Romania. Hello, Dr. Anita. Are you ready with your presentation? Hello. Hello, Dr. Anita. Are you ready with your presentation? Hello. Okay. I think let us wait for Dr. Anita to join. Meanwhile, we'll share this Dr. Anita's presentation from our end. Thank you. Hello, Dr. Anita. Hello,
Hello,
Dr.
everybody. I'm
Yes.
Anita Vishan from National Institute for Laser, Plasma and Radiation Physics. And in the next few minutes, I'm going to talk about my presentation, our work related to implants coatings deposited by maple, and these implants considered special because are based on the natural and renewable resources, namely lignin and aloe vera. And I want to insist, because I know the time is limited, but on the principle of the method, but I'm going to talk a little bit about our findings. What we have done, we deposited the thin films using krypton 4 laser, excimer laser, and the obtained thin films were characterized by physical-chemical analysis, and also in terms of biocompatibility, antimicrobial properties, and even on we studied the stability of obtained films in simulated body fluids. So in order to do that, first of all, our intention was to check the integrity of the obtained thin films, and we did that with the help of FTIR spectroscopy. And the results, the findings, entitles us to conclude that the method used assure an unaltered transfer of these fragile, delicate materials. We did also, Raman, I don't know if it is in this poster, because unfortunately I'm on another conference and I'm talking from my telephone, so it's a little bit strange, all the situation. But about the Raman analysis also supports the FTI results, because revealed also the organic material, and complementary we performed some XPS spectra, which revealed also the presence of the transitions polymeric blends. Next, we checked antimicrobial activity of the three tested recipes, and depending on the desired application, we can make a compromise, selecting the best recipes. In our case, for now, hydroxyapatite lignin aloe vera recipe 2 showed that inhibits the most of the tested gram-positive and gram-negative bacteria and fungal. So next, for the selected recipe 2, we checked the biocompatibility of the obtained influence, and we did that. And one notices that we obtain an improved biocompatibility compared with the titanium control. And when we co-culture osteoclast cells. We also check, I don't know if these findings, because are very brandly new, we succeeded to put in that presentation. We performed some studies about the stability of the deposited films in simulated body fluids, and interestingly, one notices on a weight gain, which supports the hypothesis of biomineralizations. And this idea was supported by some analysis we performed on the deposited films after immersion at different degradation time in simulated body fluids by UV and by FTIR also. And to sum up, I can say that we demonstrate the viability of the maple technique to deposit unaltered some delicate materials, and we also have in mind for the future to introduce some therapeutic agents like anti-inflammatory maybe. And I would like to thank you for your attention and for a chance to present our work.
Thank you, Dr. Anita, for your wonderful presentation. Does anyone have any query?
If everybody needs to ask me something, please write me. I put my email on the poster, and I will be glad to discuss. We are also open to potential collaboration, and just can wait your queries if there are any. Thank you once again.
I hope there are no queries. Thank you, Dr. Anita, for your wonderful presentation.
Thank you.
Thank you. Okay, the next presentation is a video presentation by Dr. Yes. Okay, the next presentation is the poster presentation by Dr. Gabriela Todor from the Military Technical Academy, Fernando I from Romania. So we will play the video from our end. So if you have any queries regarding the presentation, you can reach our program manager. So give me a minute to play the video from our end.
This conference will now be recorded.
And
Okay.
so then
Yes, yes.
the video, you then will be playing the film. So when I say, and here is the presentation film that will help the discussion, and then if you can play that, then.
Okay. Okay. So we'll share the screen from our end. Give us a minute.
Hello?
Hello, Dr. David.
Yes,
Yes,
hello.
yes, we are trying to share the video, but I think there is an issue. Kindly give us a minute to share the video.
Yeah, well, the video won't be playing until I've spoken. I need to speak for about three or
Sure, sure,
four
you can.
minutes.
Sure, you can speak.
So tell me when you want me to start because I don't know who's listening.
Okay, okay, give us a minute. We'll share the screen from our end. I'm doing it right away.
Hello?
This conference will now be recorded.
Hello?
Hello, Dr.
Hello?
Hello, Dr. David. Extremely, we apologize for the thing. We are working with that. The audio is not. We are
The
unable
audio.
to share. Yeah, we are unable to share the video along with the audio. So please give us a minute. We are working on it. We are extremely sorry
What
for that.
about the people who are waiting? Or what about the people who are waiting? Are they aware of a delay?
Yeah, we are extremely sorry for that, Dr. David. We're working on it. Kindly give us a minute.
I'm sure the
This
technical
conference will
team.
now be recorded.
Hello? I'm repeating myself potentially
This conference
for
will
large
now be
industrial.
recorded.
But I have recently decided to focus on nanotechnologies and working with artificial intelligence. The system I felt was needed for medicine in general and hoped that I would get the endorsement for that. But my main focus as a technical guy or as an entrepreneur and inventor was to look at bringing these facilities closer to the community so that patients do not have to travel to hospital and the journey there and back and the parking and all that goes with it, the stress that the patients are put under by going to hospitals. And I wanted to develop a tabletop system that could be easily located into a doctor's surgery, wherever that may be, and therefore cater for the local patient community that the practice services. So this is the design, and it is designed now. We're going to be building 2 prototypes, and I just wanted to introduce it at this opportunity I've been given to let toxicologists, pharmacologists, scientists, medics, specialists. I'm not a medical man. I have an understanding which is generic. So if you do have any questions for me at the end of this, please bear in mind that I am not a medical doctor. I am a scientist from a point of view of technology, making things happen, the machinery, the systems. So this is a system technology that is in nano form, and it contains a desktop conveyor which is nano and driven by a technology I've already received international acclaim for, and it's intelligent intrinsically itself. So the actual conveyor moving the Petri dishes will automatically have biometric details of the patients and the samples that each Petri dish is carrying. So there's no potential for confusion. And As those petri dishes are then loaded by the nurse in the practice room at the surgery, we can then position them underneath the dispensaries. On this animation that you saw, I just show three, and they are giving you an indication of local dispensaries that have got capillary tubes inside, and there are many capillary tubes inside those dispensers, and they will be loaded with proteins, enzymes, minerals, and any other ingredients that the doctors and the specialists want to trial. So in effect, what I'm offering here in this application of the technology is the ability for patients to submit a swab with a blood sample that's taken at the surgery, and whilst they still are waiting in the waiting room at the surgery, the practice nurse and the doctor can then check to see what the DNA is of the patient, what is their human physiology, to gain better understanding of any weakness in their human condition, and to try to balance that knowledge and information with a cocktail of drugs that will make a chemo package that will be tailored to the individual. So it's design a drug system really. And this is moving away from one size fits all. As an example, in my relatively new learning of your world, I realized that taking breast cancer, for example, most women are prescribed tamoxifen, which is very useful, very helpful, and does make a big difference to patients' conditions, or cures them, or improves their condition, but it doesn't suit them all. And therefore, I felt there was a need to look to identify which elements of the tamoxifen are going to be harmful to a patient and which could be substituted by some other nutrient or ingredient that the scientists and professors of cancer, for example, like Professor Flavin, who you just heard speak, um, and for them to trial a different variety of cocktails of enzymes, of proteins, of nutrients, of minerals, new plant extracts, and things we are going to be introducing from the ocean. The ocean has many secrets to divulge for us, and we're looking into seaweed, working with the company on that. There's different varieties of seaweed which have properties that have yet not been fully exploited. This is true with bryophytes and other plants that, again, fungi and other areas of agriculture that will be capable of introducing new features that could balance out a drug package, and to make certain that we give each patient the best possible forecast of the ingredients that will match their own personal DNA. So this is new technology. Forgive my lack of ability to communicate this medically better to you, but as I say, I'm a technical man, and micromedics is venturing into this world of yours. So I want it to be focused more on doctor surgeries, so that we can localize these things and to prevent the hospitals having extra pressure of people going in for tests as they do every day. In England at the moment, our NHS system is under great pressure, and I'm sure that other countries are experiencing similar problems. So the more we can bring to bear with the GP, the local doctor who knows the patient, there'll be a more relaxed atmosphere and also take the pressure off the hospitals. So the system has been proven in macro. I have developed intelligent conveyors that work in baggage handling, meat processing, and a variety of manufacturing and distribution systems in the commercial world. This is my first foray into bringing everything down to nano size, and it is hoped that when the prototype is built in the next 6 months, we will be able to trial the variants that I have described that these intelligent dispensaries will dispense. Linked to AI, of course, we're going to be creating a database, and that database will be drawing in papers that have been written by doctors and scientists over many years, and gradually we'll be bringing case histories and studies of various cancers. Another disease, we're looking into motor neuron disease and other life-threatening or life-limiting diseases, and also diabetes and so forth. We're beginning with cancer, and we're beginning with breast cancer, which Professor Flavin felt was the most sensible one for us to start to trial this for. But in time, we hope to be able to make this equipment benefiting all illnesses that are debilitating or life-threatening. So I think you've got the understanding. I'm not going to talk forever. I am quite happy to take any questions if you wish to raise them, but bear in mind the technical questions if that's what you wish to present and not medical ones.
So that is a wonderful presentation by Dr. David Japscott from Engineers Group of International Limited, United Kingdom. So if you have any questions, you can ask Dr. David. He's available here.
One thing I forgot to say actually, which I think is important, the materials that we're using to build these dispensers and the track and the dishes, the petri dishes, are all going to be made out of materials that are recycled plastic that will be impregnated with antibacterial agents such as microban, and therefore we can keep the whole system totally sanitized. And the system is very easy to break down and to give a thorough cleansing if there is a need for that. It's designed in such a way that it can be easily taken apart and put back together again. But it will always be impeccably clean and sanitized and with antibacterial agents. So, having not seen any questions raised, I will assume that you are more obviously medically inclined, and I thank you for the time you've allowed me this afternoon. And if you should think of any questions after this presentation is completed today, I'll be more than happy to take them, and my details can be found. I'm sure you'll see them within the presentation pack that you've received. Thank you so much for your time and for your interest. Good afternoon.
Thank you, Doctor. Thank you, Dr. David Japscott, for your wonderful presentation. So, by this, we move on to the next presentation. The next presentation is a poster presentation by Dr. Gabriela Toder from Military Technical Academy from Romania. So we will share the screen of Dr. Gabriel from our end. Kindly go through the presentation, and if you have any queries, you can reach our program manager. Thank you, everyone. That is the presentation by Dr. Gabriella Toder. If any questions regarding the presentation, you can reach our program manager and she will guide you accordingly. So by this, we come to the end of the session. So we came to the end of the day one webinar. I would like to thank all the attendees, participants of today's conference. Hope you enjoyed it. And request you to attend tomorrow's session too. And thank you. Have a nice day. Thank you, everyone.
Thank you. Thank you. We'll meet again tomorrow.
Sure. Yes, we'll meet again tomorrow.
Okay.